somebody should, the organizers. Okay. So, welcome everybody. And so I'm very happy that finally some mathematics is taking place here. Usually we have meetings about, I don't know, agriculture or forests and so on, because the tradition of this academy in recent years has been that one. Unfortunately, it's not my mathematics, so I'm very happy, but I understand even less than in agriculture today. Okay, so in any case, what happened was very strange. A few months ago, Thierry Paul, whom I didn't know at that time, came with my old friend Italo Dolcetta, who was my, in fact, we were together at the university in the same year. And they came, Dolcetto lives nearby, and they came and said, oh, okay, I want to introduce my friend Paul, and so on. And so we started discussing, and eventually he explained me that he was going to spend some time in Rome because they had created something called Hypatia Lab for mathematical sciences, right? Which was created as a result of some agreement between CNRS and INDAM. INDAM is the equivalent of CNRS just for mathematics, because the mathematicians wanted to be alone. They don't want to mix with the other scientists in Italy, I mean. So he proposed that the Hypatia Lab should interact with the Academy of the Forty. Since I was a bit frustrated because, you know, I accepted to be president, but no mathematics whatsoever. I mean, I was hearing always about, I don't know, chemical abstract of restoration of paintings or things like that. I said, okay, let's go. I soon realized that I was completely incompetent in the matters that he was interested in, but still I said, well, organizationally I can give a hand. So what happened was that we started thinking about some activities, and this is the first one. And I think there is another one which will follow. I hope there will be more, because, you know, at least maybe also something in algebraic geometry or algebra or whatever, so that I can enjoy more. And so the one that follow will be on July 15th, and it was a colloquium talk, I think the first one in some series you are organizing, which will be given by Michel Tarragan, and he will call Chaining a Long History.
Exactly.
Yes, correct? Okay. So I think I have nothing else to add. I don't want to bother you. We are already late. So have a nice workshop. I will allow myself to follow the first lecture. I probably run away after that because I won't understand anything, but okay. And so have a nice day. The beginning is nice. I don't want to bother you about the history of this academy. Just let me say that it's the oldest academy which has been in activity in Italy in the last 250 years, more or less. I mean, it's much older than the Accademia dei Lincei, which was founded before, but then since it was financed by a single person, it ended its activity very soon, and then it was reopened later on. So have a nice couple of days, and you are the first speaker. Okay, coming in.
Yes. Does it work? Yes. Perfect. So, first of all, thanks for the organizer for giving me this opportunity to present work we have done in the last 10 years at ENS de Lyon. Together with many people, and one of is Thierry Doxois, who all knows. He should be here, but he will arrive maybe around noon. And yes, since we talked about this yesterday, I wanted to show him a nice movie he has done on dead water experiments. So it's not the topic of my talks today, but this experiment with a small boat that is on top of water, and you can see that the interfacial wave between two fluids can stop the boat at some time. And that's a production of a dead water phenomenon. So the goal of this lecture today is to discuss, we asked me to give a detailed presentation of the annual review of fluid mechanics paper that we have written with Thierry in 2017, which is called Instabilities of Gravity Internal Wave Beams. And it's a discussion where we have theory and experiments. So I'm doing most of the experiments, so I will present the experiments, and I will discuss some of the models we have built with these experiments and to confirm the experiment. And I'm free to answer all of the questions, and please ask me many questions. So in this paper, we discussed mainly triadic resonance instability in 2D experiments. And we also discussed mean flow. I have decided that I have no time for mean flow, but I will spend more time on what's new since 2017, and I will discuss some development of TRI in 3D, the comparison between internal wave and inertial waves. I think it's interesting to discuss this. Some other shapes, some wave turbulence, but I will go step by step. So since I have two slides about geophysics, it's a discussion about instabilities in geophysical flows. So I think everybody knows here that internal waves are very common in the ocean. So internal wave develop in stratified fluids, and stratification is what you have, should be here. Here you have that the temperature depends on the depth, the salinity depends on the bed, and it leads to a dependence of the density with depth, which is this way, and we will construct the buoyancy frequency, which is a measure of the stratification. I will come back to this soon. And here in this recent paper, you have the kinetic energy of internal waves at the tidal frequencies, and you have seen many kinetic energy that are localized near topography. So you have a closed link between topography and internal waves. And that's to you have this in this picture that internal waves are very important for climate model, and you have many generations of internal waves going from topography, as I said, from tidal flow. You have also some winds that create internal waves, wave-wave interaction, and all together, this is very important. Yes? I think this is a it's a good question. I think it's in this case. So, for example, what you do usually you have some points where you have the measure of flux of velocity field. You look at the frequencies, at the tidal frequencies. So you using Fourier transform of some plot, and then you use some numerical simulation to reconstruct all the wave fields. So you have both near the topography, you have more waves. So you have different points in the.
What you measure is the velocity, not
No, you construct the kinetic energy, so the velocity squared, and usually you miss some data, and that's an important point to how to reconstruct all the data for the whole ocean, since you have few points. And that's what is believed that is important for climate systems. That's all the wave-wave interactions, all the mechanisms. So it's and the other one is what's seems to be important is mixing. So internal wave can help for mix the ocean at low scale. So you have some energy transfer between large scale to small scales. And these small scales can change the background potential energy, which results into mixing. And that's one of the mechanisms we want to study, how we can go from large scale to small scales, and how these small scales breaks and generate mixing. That's one of the goals in the group in Lyon to study this experimentally. And different mechanisms has been proposed. That's wave-wave interaction. That's what I will discuss today in instabilities. That's also the reflection of topography and so different instabilities that are responsible for this transfer to large scale, global scales, for example, the tidal wave, to small scales where mixing is possible. And this mixing is used to parameterize climate model or global circulation model. So that's why it's important to really understand how large scale can mix, how large scale goes to small scales and mix the fluids, because it's not resolved in a numerical simulation. And that's how, why it's important to study this kind of phenomena.
And then if you would like to use it as an application and to understand also the feedback from small scales to large scales.
Yes, yes. Yes, you want to understand, to do both. In fact, when you have wave-induced mixing, then the mixing will change the behavior of the wave, and you want to see how it will, the wave will adapt to the change of stratification, and you have a double coupling phenomena. I think what I want to do is that if you have this stratification, this large scale, you create this mixing, you will change the stratification, and then you do a two-way coupling in this case. And for the moment, the parameterization is an ad hoc parameterization that is not completely clear. And so these two slides was to explain what was the goal of the study of instabilities of internal wave experimentally, is to have a simple laboratory experiments where you can generate the internal wave as clean as possible with no other phenomena, and generate interaction the way we want, and then create the mixing, and to understand, okay, this phenomena leads to this mixing. That's the goal. Okay. And I will go to the basis how we have, I will start to explain how the experiment was built in our lab, and how with these experiments we can have instabilities. So I will start, so I think everybody knows what an internal wave is, I guess, I hope. Hmm? Yes. Okay, so an internal wave, so you start with stratification, so the density increases with depth. You have fluid particles that move out of its equilibrium position. So in this case, the particles is denser than the surrounding fluids, so the buoyancy force acts as a restoring force. And the same if the fluid particles is below its equilibrium position. So now you have the buoyancy force act also as a restoring force and pushes upward the fluid particles. And as a result, this is a competition between buoyancy as a restoring force and inertia. And you generate, in this way, internal gravity waves. And with the characteristic frequency, which is the buoyancy frequency, which has this shape, we'll notice the stratification. This is a mean density. And in this frequency is 0 for homogeneous fluids, and then is very large if the stratification is large. So that's the basis, and I will just explain what is the equations we use to explain the experiments. So the basis of equation, we will use a velocity field with no mean flow. We have the pressure field, we have the density field, which is separated into three components: the mean density, the stratifications and the perturbation to the stratifications. And the internal waves is this perturbation of the pressure field and this velocity field. We use different equations. So you at the first order the hydrostatic approximation, which relates this to this constant. You use the Navier-Stokes equation under the Boussinesq approximation, meaning that the only part where the density appears is in this gravity term. You have the mass conservation, and you have the incompressibility. And I have added the dissipation through viscosity and diffusion. And in some part of the talk, I also discuss with the buoyancy field, which is just the density field written in another way. That's just a way it's changed. And I will just introduce some dimensionless number to discuss which case we studied. The first one is the full number, which compared the advection to the time of the wave, which is called the full number, which relates this to quantity. And in the wave regime, the full number is smaller than 1. So we have this term that dominates. The second term is the Reynolds number, which compares this advection term to the dissipation, which is written in this simple way. And weakly interacting nonlinear gravity waves, we still have many waves, so small full number, but we want to increase the advection term, so we look at large, not so large Reynolds number if we want to be weak, but we increase the Reynolds number. And with this, basically, these 3 time scales. The last one, and I will remove one of the parameters quickly, is the Schmidt number. The Schmidt number compares the dissipation through viscosity and the dissipation through diffusion. And for salt water, which is the water we will use in experiment in the ocean, nu over kappa is of the order of 700. And basically, we will consider that kappa is 0 in all the equations. And we'll keep only one dissipation term, which is this one. Okay. So the first step is to go to remind what's inviscid linear equations. So I have removed advection. I have removed the viscosity. And you have these 3 equations. And the solution is a superposition of plane waves, which can be written in this way, exponential I omega t minus Lx minus kyy minus mz, with the dispersion relation, which is written this one, which where k perpendicular is the combination between L and ky. And you have these dispersion relations, which leads to this famous shape, which is the Saint-Andrews cross. So if you have an oscillating cylinder at a frequency omega, you have an internal wave field, which has this cross shape. This is an experimental movie where you measure here the gradient of density. And so the propagation, this dispersion relation has some properties that are interesting. First, you have a link between omega and the angle of propagation. So omega is always smaller than n, the buoyancy frequency. You have the property that the phase velocity is in this direction. You can see in this movie. So red means larger stratification in the horizontal direction, blue smaller. So the phase is going in that direction. The group velocity is going into that direction. And theta, the angle here, is the angle between the group velocity and the horizontal. And the last thing that is very important is that the wavelength is not controlled by the frequency, but it's fixed by the boundary conditions, which means that's important for experiments to build the experiments so that the wavelength is controlled. But that's also a key parameter, so if you impose the frequencies, you doesn't choose the wavelengths. It can be the forcing, it can be the reflection. Here in this case, for example, the shape, the size of the waves are fixed due to the size of the cylinder. So I mean that this is a combination, this is a wave beam with a combination of different wave vector. And this combination is fixed by the shape of the wave, of the cylinder. And and so the boundary condition, you can choose a boundary that is moved and you will choose the forcing in this way. But if you have a wave that is the reflection of a wave on an inclined slope, you will change the wavelength.
But is it due to the size of the cylinder or to the displacement of the cylinder?
Here it's due to the, it's related to both the size and the displacement. But if you have large, for example, if you have very large cylinder that oscillates, you will have a double peak wave corresponding to the critical, it's linked to the critical slope of the cylinder. If you have a small cylinder, you will have other phenomena near the boundary layers, near the cylinder that will change the wave beam. So that's why I mean it's due to boundary conditions. Here it's the forcing, and now if you have other boundary conditions in the problem, for example, if you have a tank and you oscillate the whole tank, the wave field will also depend on all the boundary conditions of the tank.
What is the forcing equation?
In this equation, for propagation, we don't impose the forcing, but now if I haven't talked about boundary conditions, you can also. Usually, in all the experiments, the forcing is fixed by the boundary conditions, And this will therefore impose the choice of the geometry of the tank we'll study in experiments, also the choice of the wave maker we have used for laboratory experiments. So in this case, so this is written in 3D, this is done in 2D. Just in 2D, because I will use this equation in this way. In 2D approximation, I introduce the stream function. I assume ky is equal to 0 in this case. And so you introduce the stream function written this way, and you have so for the wave, the equations is simply this form. And for internal wave beam, you have pure 2D motion. So if you impose ky equal to 0 and vy starts to 0, it stays at 0. So you have a pure 2D motion in this case. And usually in experiments, we don't have pure plane wave. So we use the results of plane wave, but we don't have plane wave. We have usually wave beams, which is what you have in this movie. This is a wave beam. And so wave beam, it's a superposition of linear solutions at the same frequency, same direction of propagation. So if you impose the frequency, the CG is fixed, and you have different wave number of same sign. So the wave beam has this form, this mathematical form, and depends only on okay, on eta, which is the transverse direction, and does not depend on psi, the direction of propagation. So now we have, I have introduced all the ingredients for linear wave. In laboratory, first we start with doing a stratified fluid, and it's easy to do linear stratifications in experiments using what's called a double bucket method. We start with 2 buckets, one with salt water, one with fresh water. We mix with time this fresh water with salt water will become more and more salty, and you create in the tank a density which is linearly dependent with Z, leading to a constant buoyancy frequency. So that's easy to do. Usually in experiments, we have at the bottom and at the top small boundary layer with a mixed fluid, which can change a bit the wave. So we don't exactly know the height of the tank, and this 2 mixed layer increases slightly with time over 1 or 2 days because of some. Yes, it's easy. In fact, if you have one flow rate, if you impose a pump here and a pump here, you choose the flow rate here, the flow rate here, and you can design the stratification you want. Yes, we. Yes. So it depends then the dependence of n compared to so if n depends slightly with z, for example, in this case the direction has. So if you have stratification, so if here I will write, okay, with Z, this is a linear stratification. Now if you impose something which is like something which is like that, for example. So here it's omega n is smaller and larger. So the propagation will go like that. We follow slightly the wave, and you have at each z, the dispersion relation is satisfied at each z. This is the case where the stratification does not depend strongly with z. If n depends strongly on z, you have other behavior. And you have to take into account in these equations. But this relates that the derivative of n compared to the vertical wavelengths. And yes. But we have also realized experiments where you have like density field, which is like that. And then here you have the wave goes like that, some reflection. And then in this layer, it depends. Either you are stratified or non-stratified. If you are stratified, you change. You can change the angle of propagation if omega is smaller than n. Or you have evanescent wave. And in some cases, you have some tunneling effect that is possible. And you can have a wave here. And you have some transmission coefficient between the top layer to the bottom layer. And this can be... and it has done experimentally by Tom Peacock. And we have done some experiments also in Lyon. This kind. So it's easy to do nonlinear stratifications. But then you have many experiments where you have a Picnoc line, which is classical in the ocean, and look at the Picnoc line and the interaction between the Picnoc line and the... you see really like a boundary, but not a rigid boundary, so you have some motion at the boundary. but no, it's not like. Then it depends on the stratification. If you have a strong stratification, it can be like a rigid boundary. For example, if you have a mixed layer like that, and otherwise you have small small widths where you have an internal wave that's a combination between a reflected wave and the incident wave. In this case, what I call tunneling is that here n equal n 0, here n equals 0, and 1, for example. And you have, so if n equals 0, normally you have no propagation of internal wave. But what you see in experiments is that a wave, you can see a wave below this depth with no stratification. And this is due to evanescent wave. So if n is strictly 0, you have nothing. But if n is very small, you start to see some wave that appears below this mixed layer. And I call that like a tunnel effect in quantum physics. And because you have some, you can calculate the transmission and the reflected part. But in fact, what you have, this generates this part through evanescent wave. So you can see some motion here, but no propagative wave. And if the length of the distance for the evanescent wave, the characteristic distance, is related to the width of this depth, you can create a wave below. And this, we also observed it in experiments. Just, we started with the linear stratification. We had some mixing at some time. And then at the end, we saw we had mixed layer in the center. And so the wave is changed. And all the instabilities is modified. All the, you can yes, it's a pure linear phenomena. You can you can calculate it analytically, and it's close to experiment. Okay. Okay. And then, so that's the stratification, how it's made. Now the second is how do we observe the different waves. So as I said, the wave, you have either the pressure field, the velocity field, or the density field. So for the pressure field, we do no measurements of the pressure field. We study either the velocity field using a PIV or a density field using these three techniques. Just to explain, I will start with the PIV. So PIV, so we have put small spheres in the fluid, which are, and we use a laser to enlight these particles. You have many particles here, and you can follow the motion of these particles and relate this to the velocity field of the fluid. You follow a group of particles and you have the velocity field. You can do 2D or 3D. I will mostly focus on 2D PIV. And this is another case where you can see you have the fluid particles, and this is the case of the mean flow we studied with two vortex. So it is in this plane with no boundary on the side, and you can see that the wave generates a mean flow, and you have some recirculations with big vortex. And that's now easy to do in experiments. And the second one is to use the study of density field. One is to use dye lines. So we enlight some particular density with dye. Here it's rhodamine in a tongue that was trapezoidal in this case. And you had this. I wanted to show one movie of attractors because I think it's a beautiful experiment. And you can follow the density, and you can see the motion of the waves in a pattern. And the second one, where you can follow also the density field, is to use also with dye using laser-induced fluorescence. We put a stratification of dye which is the same as the stratification of density. You highlight it, you use a laser with this dye. You use the light coming back from the dye, the emitted light, and with some filter you can have the density field at all depths. So here I have chosen only few lines, and you can combine this with PIV to have both density field and velocity field. So we have few experiments with this. In this case, you have the link between, here it's a propagative mode. And we have some density fluctuations, density motion with velocity. This can be interesting if you want to study both at the same time, how the density how the density and the velocity field are related. I will come back maybe at the end to this. The most used techniques for all the talks is synthetic Schlieren experiments. So in this case, you have a dot pattern behind the tank. You look through the tank. Okay. And you can see some motion. I don't know if it's visible. You can see some motion of the dot through, because there is an internal wave in the tank. And you use some processing, which is the same as PIV, to measure the density field. You measure some correlation between the image with and without wave, and you have the displacement of the dot. And this displacement of the dot is related to the gradient of index of refraction, which is related and proportional to the density gradient of the density gradient integrated over the whole width of the tank. The advantage of this technique is that it's something which depends on the vertical velocity and also on k. So the displacement is larger for small scales, so for large wave vector. So it means that for all the experiments I've shown in instabilities where you want to see the small scales, it's the synthetic Schlieren help to see the small scales compared to PIV at the first step. But you have less access to kinetic energy on all these other measurements. That's the two. Yes? No. What you have put a dot, you print on the paper, many dots, and you look through the tank. And this helps to, and you have access to the gradient of density, in this case, integrated over the whole width. Okay, last thing of what experiments is how do we generate waves. And so I have already shown an oscillating object, which is a wave beam. If you have you can oscillate the whole tank, and you generate global modes that depend on the geometry of the tanks. Here it's a rectangular tank, so you have like sloshing modes. If you have a trapezoidal tank, you have attractors. You have also, if you oscillate only one side wall, and we have done many experiments with this, you have propagating modes, which has this shape, which is the superposition of one wave going in that direction and one wave going in that direction. And you generate a mode that has a cosine shape over the whole depth and propagates in that direction. And how it's done, for the case, we use some disks that are off-centered hole and that oscillate. So we put many disks like that with different phase like that. And if you compile all this, you can create the shape you want in the tank. And the shape you want here was to mimic a plane wave shape for a small, over a small width. And it's what is done here. You have, here in this case, here it's one wavelength. So you have like a localized internal plane wave. So I have 3 wavelengths, and then, but in these 3 wavelengths, you have a plane wave. The weakness of this, that the amplitude cannot be varied during experiments. So if you want to change things, you have to redo everything. So the stratification. But there are new improved systems. So in Lyon, you have 50 motors that can control each plate, which make it complicated, but it's possible. And you have also what's in Cambridge, same system with many motors at the bottom of the tank. And they call this the magic carpet, and they can create the wave they want. So you create the boundary you want, so you can study this experimentally, so that helps. Okay, and
How do you relate this to the stratification profile?
this, we don't relate it to the stratification profile. We create this, and we fill the tank after. So we have n fixed in that way, and this shape fixed in. Okay. Okay. Should be this. And so if this, you put the generator on the top, you have this wave maker and create a plane wave with a characteristic wavelength of 3 centimeters in this case over 3 wavelengths. And you have all the features that have already been discussed. So that's how we have done all the experiments, and I have all the ingredients to start to study the instabilities. Okay, so for the instabilities, I come back to the initial equation. So I have this equation for the stream function, and I add the viscosity and the 2 nonlinear terms that are written with 2 Jacobian terms. And with the property that if you have a plane wave, you can calculate that the 2 Jacobians are strictly equal to 0. And so the plane wave is solution of the nonlinear equations for any amplitude. And it's because you have this is direct, and you have a polarization relation between the buoyancy and the stream function. And using these 2 relations, you have these Jacobian that are equal to 0. For wave beam, you have also exactly the same. Since the wave beam is written in this way, has a sum of different wave vector, you have no dependence in psi. Therefore, there is the Jacobian terms are strictly 0 for both cases. So for wave beam is also solution of the nonlinear problems. So that's the first step. But it's not necessarily a stable solution. So, and that's what was observed in experiments. After sometimes the same experiments as before, we force at a single frequency, and we start to observe some disturbances in the wave field. Disturbances with different direction here, and you can start to see some waves here where there is no forcing. And the question of this is related to 3-wave interaction. So if you have 2 waves in the tank, through the nonlinear term, you have like a forcing term, which has the sum of 2 frequencies, the sum of 2 wave vectors. So if the linear relation is satisfied, you this is what is called triadic resonance instability. You have omega naught equal omega 1, omega 2, the sum of the three-wave vector, and the dispersion relation for all the waves. So that's a triadic interaction, and the question is, is it what we observed in experiments? So we start from this. At a single frequency, we observe this phenomena. So we have a primary wave, and do we have spontaneous emission of two secondary waves with these relations, temporal resonance, spatial resonance, and the three waves satisfy the dispersion relation? That's one of the questions. So we look at both cases. So first of all, we look at the time evolution of the frequency spectrum. So we have the frequency spectrum as a function of time. We start at the beginning with a single frequency, and after sometimes, two frequencies appear in the tank. Here is what you observe at this time. So you can see the primary wave and two secondary waves, clear secondary waves. And if you look at the values, you can do this plus this equal to these frequencies. So you have a temporal resonance condition that is satisfied in experiments. The second one was to study the wave vector. For this, we use the fact that if you have a single frequency, you have 4 directions of propagation. Each of them corresponds to one k. So you can separate k, kx and kz to these positive and negative values. So you have 4 quadrants, 4 localization. So for 2 negative kx and kz, you select only this beam. And you can separate the 4 beams by selecting the sign of kx and kz. Doing this in experiments, so if you filtered at omega naught, you have this wave, which is the primary wave, with a single k naught, this like this. For omega 1, you have this case with k1 like this, and the group velocity. Here the group velocity is like that, here it's like that. And in this case, the group velocity goes into that direction. So I measured the k. So in this case, I filtered at omega naught. Then in this case, I use a Hilbert transform. So, and I filtered. So I have the whole wave field with time. So first of all, I filtered the wave field at omega naught at each frequencies. So I select these frequencies and I filter the wave field at these frequencies. If you filtered, in this case, if you filtered at each frequencies, you observe this is one snapshot, and you observe this, this, and this. Then to measure k, I use the Hilbert transform and I compute the phase of the Hilbert transform. And the phase of the Hilbert transform gives the value of k, and gives the quantitative value of k. The phase is like Lx plus mz. So I measure L and m with linear fit, and I have the value of k. And I have also the direction, because in this case z was negative and kx was negative. And if you look at this at omega 2, you have only wave vector with both negative values with this direction. If you filter with other k in other, so I have I'm in this case for omega 2. And if I filter like that, I have nothing. If I filter like that, I have nothing. If I filter like that, I have nothing. No signal. So in this way, I have been able to measure each k. I can also do a spatial Fourier transform, but using the Hilbert transform is a bit more precise than the Fourier transform because I have no many wavelengths to compute to compute a nice Fourier transform. So I have the quantitative value of k, and if I do this geometrical shape, I have this spatial resonance condition that is also satisfied. And the next step is that can we, so in this case, can we quantitatively predict what's the value of omega 1, K1, and omega 2 and K2? I know that I have the spatial resonance. Can we predict their value? Is it only one value or is it many values? So if I have the quadratic nonlinearities, I have these conditions. So I have 6 unknowns on 5 equations in 2D. So I use, I have plot where many possible triads can exist that are solution of this problem. This is what's in this shape. So that's the position of each tips of K1. So in this problem, I fixed K0, and I have K1 that can be all these lines, and K2 is K0 minus K1. So I have many possible triads in the problem. There are also, here I fixed plus with a minus sign is also possible, but it has been shown that is neutrally stable. So all the growth rates with a minus sign here will get to no instability. So that's, and it has been shown. So that's why I focused only on this case with omega 1 and omega 2 positive value. And the next step is, okay, now we have many, many possible values of K1 and K2. Can we say which one is the one? Yes. Yes. You do the same computation. In fact, yes, you have a minus sign, and you do the same computation as I will present, and you see that sigma is always negative, with dissipation or 0.
But you cannot anticipate this.
Yes, I think you need to know. You can do it without dissipation, and without dissipation is the growth rate is strictly 0. So this is the calculation I have performed for this. So I look at a solution of the form that the sum of 3 waves for the stream function, for the buoyancy. I inject this 3 form in the Navier-Stokes equation and in the mass conservation, and I consider the nonlinear term as forcing terms. And the system is resonantly forced if I have this temporal resonance, spatial resonance, and the dispersion relation for the 3 waves. So I have made some approximation to calculate the growth rate. The first one, I impose that I'm looking at the beginning of the instability. So I'm looking at the beginning, I have only the primary wave. So I assume that the amplitude of the 2 secondary waves are very small compared to the plane wave, the primary waves, and therefore I also impose that the amplitude of the primary wave is constant. The second one is I impose slow variation of the amplitude, meaning that the variation of amplitude is very small compared to omega times psi. And at the first, I solved the problem at the first order, and I have the polarization relation, which is still valid, and I can use the derivative of the primary relation for this, which relates dot r with dot psi, which is useful in this equation. I inject all, so I assume that the variation of the amplitude is balanced between a competition between viscosity and the nonlinear forcing. So I have these three terms that have the same scale. And if using all this approximation, I can get the amplitude, the equation for the amplitude of the secondary wave, which can be written like that in time. Yes. Yes.
Of course, it doesn't satisfy.
Yes.
So you seem to say that it satisfies this when you do something or when something is small. So what is a small or large parameter?
So in this case, so what is small? So in this problem, so I do a multi-scale analysis in the problem. What is small usually is the amplitude of each waves. So I assume that I have small Froude number. And if you do small Froude number, you do a development in the Froude number. And at the first order, you obtain the dispersion relation for the three waves. And at the first order, you have, so the dispersion relation, remove this, and this. And you have still two solutions, one with psi. And you have, at the first order approximation, this is a Froude.
So it's a small amplitude.
Small amplitude approximation.
Also small energy.
Yes, it means small amplitude. In fact, the two secondary waves emerge from noise, so they have a small amplitude. And so in this case, yes, in this case, yes, these terms, we assume that this evolution in amplitude for the secondary waves are forced by the interaction of the primary waves with the other secondary waves, which is also in the noise. So that's so it's a subtle point, but that's how it's done. That's how we do. So that's why we do a multi-scale analysis, and we assume this, and we say to include the viscosity, that the viscosity will modify slightly the growth rate in the problem. So that's why I say these three terms have the same order of magnitude, but are very small compared to the first order equations. That's why I said all of the waves are still in the dispersion relation. And at the second order, I look at the amplitude evolution. And in this case, I have these solutions in the problem. That the equation for the amplitude of the secondary wave, which is the increase of psi, the change of the amplitude of psi 1. You have the same equation for psi 2 with another coefficient I2. It's the same shape of the coefficient.
Kind of quadratic approximation.
Yes.
Again, in terms of the amplitude.
Yes.
Okay, that you don't write in the paper.
We don't say that in the paper.
No problem, because it's so for you.
Yeah. Yes, it's a.
We put an epsilon.
Okay. Oh yeah, we didn't put an epsilon in the.
Yes, it's an in fact, yes, epsilon, or in one paper, they put a full number and they develop in terms of foot squared with a small full number, which is the parameter epsilon. It's possible, right? But you obtain this equation in this approximation. And then to go a bit further for the comparison with experiments, you have this. You assume psi naught is constant. You combined the equation for psi 1 and psi 2, which is written psi plus or minus here, but it's psi 1 and psi 2, or psi 2. This is the complete equations for the amplitude of psi 1 and psi 2 for the two secondary waves, which can be solved with an exponential sigma t. You have also plus exponential minus another sigma. And sigma is in this shape. With no viscosity, you have only this amplitude, which is psi naught squared. And if you look now at the growth rate as a function of k1, so you're all over this curve, and you look at sigma divided by the maximum of sigma as a function of k1. For inviscid case, with the viscosity equal to 0, you obtain that the maximum growth rate is for infinite values of k. So, which means this is in this case, with k1 is approximately minus k2, much larger than k naught. And omega 1 and omega 2 are equal to omega naught over 2, which is what's called in the usually parametric instability.
So these are computations related to the equation?
Yes, this is we compute sigma using all the values that are solution of the triadic resonance equations.
Because at a mathematical point of view, it's not easy to let the dissipation coefficient going to 0 if you don't, if it goes faster to 0 than the amplitude.
Okay. Yes, I see.
In mathematical terms, the two limits don't compute.
In our case, yes, we have. Yeah. In fact, what has been done? So for this case, if you the calculation have been also done without the coefficient nu in other paper. They obtain this equation without this term, but the same equation, and it does not change in this. So they compute only this term, and they observe that the maximum growth rate is at infinity.
So just again, remarkably, if you want, I mean, it's not really a theorem. If you want to prove that the approximation is valid, you need absolutely to have a new difference. When you go to 0,
Okay.
the estimation is great. Those things maybe not.
I think I have the answer is the. I have the answers in this. Yes, in this slide. I come back to this. What has been done first for viscous case? So in fact, when I call this inviscid case, I think I put nu 10 to the minus 14 to do the plot. I think I have done that at the end. So it's not a pure inviscid case; it's nu going to 0. And in this, yes, I think so. Yes. And in the viscous case, you have a particular growth rate at finite values of k, which is in this maximum. So just before going back to experiments, the first question is that is there a threshold in the instability? So this means that you compute this with viscosity, and you said, okay, we want sigma positive, So it gives this threshold, but you can always find the combination of K1, K2, I1, A2, leading to the fact that there is no threshold. So whatever the value of psi you have in the tank, you find a combination of K1, K2, that are solution in the problem for plane waves, and the instability appears. So you have always positive growth rate for particular values of K1 and K2, whatever the amplitude of the primary wave is. So you have always instabilities for plane waves. And the second thing, I think that the maximum growth rate is obtained for a value of K which scales like psi naught over nu to the power 1/4. So that's, we plot with numerical simulation to observe this shape. And I added a line which has to the power nu over 1/4. So I played with many, many values of the viscosity, and I found this scaling laws. So this is why I said that K max increases if nu is going to 0. This is a numeric, is just a solution of these equations. And I calculate for many, many values of the viscosity. Yes, that's numerics. Okay, if I come back to experiments, so now I have the values of K0, K1, and K2. I put in the resonance localization. I calculated the growth rate for the experimental parameters. And I have these shapes. The two dashed lines correspond to the value of omega 1 minus omega 2 that are neutrally stable in this case. And you can see that the maximum growth rate on the red line correspond to these lines in this, the two lines here. And the value obtained experimentally, or localization here, localized here, which correspond to the red point in the experiment, for the maximum growth rate. So we added a large possibility. So here the growth rate is flat, so it's not clear why you have a single values of K1 and K2 that appeared, but it's what is observed experimentally, and it corresponds to a maximum of the growth rate, but not the global maximum of the growth rate. So the maximum growth rate is here, but experimentally you observe in this case, which is that the selection criteria is not completely consistent between theory of plane waves and the experiments. So in this case, I calculated the growth rate for using experimental parameters. You can see that you have two. So if I look at, you have different maximum. So the red lines correspond to the interior here. And you have a maximum, a local maximum, the growth rate localized here, and here in the black region. You have a second maximum corresponding to the exterior, to the other part of the resonance, the two lines. And the experiments that are the different arrows here, that are the experimental results, correspond to the second maximum of the growth rate, but not the first maximum of the growth rate. That's that's the first result, and say that therefore there is a difference between the theory of plane waves and the experimental results in the selection criteria. The second one is in the threshold. So I put a phase diagram with the amplitude of the primary wave, the frequency of the primary wave, and there is many values that are the cross where there is no instabilities during the experimental during the experiment, and a part where you have TRI. So it seems that you have a threshold in frequencies and amplitude, which is not predicted in the theory. That's the second result from experiments.
How do you know experimentally that you're close to a plane wave? Because plane wave is distance.
Yes, and I'm not close to a plane wave. I'm a plane wave, but only with 3 wavelengths, which is not really a plane wave. And this is why that was the first step of the comparison between theory and experiments, was to study with the calculation for plane wave, and we added something else due to the finite size of the beam, and which is the step that is just after. Okay, I will go fast on this. I will discuss slightly about the experiments for the finite size effect. So the finite size effect, so in this case, you can see that so in what we observe is that for all these experiments, we waited for a long time, not infinitely, but we see that at the end of the experiment, we see only the primary wave and no secondary wave at all. In fact,
But still the solution is not equal to the primary wave, or it's really a pure primary wave.
in fact, in this case, for example, in this case, we observe, so we have a primary wave like that, with, and we observe this wave for 15 minutes. We didn't do more experiments longer than 15 minutes, so maybe after 3 hours, a secondary wave may appear with a very small growth rate, but during the experimental time, there is no instability. And it remains like a plane wave. And for some experiments, we waited 2 hours and we see nothing in the tank. Only plane wave. Only the primary wave we impose by the forcing. And
If you compute this, the linearization around this, you find
see, if I put the linearization,
with so your TRI bubble,
for plane wave, yes. For plane wave, yes. But clearly, in this case, so this is why we wanted to show that we have finite size effect. In this case, I have the same. So I have plane waves, 3 wavelengths. Here, 2 wavelengths, and I have the same wavelengths, K0, same amplitude, same frequency, but not the same size of the wave beam. Here, 3 wavelengths, here, 2 wavelengths. In this case, we observe instabilities. In this case, it remains stable forever. That's clearly why we say that the finite size clearly matters in the time. And I will come to this later. What we expect from the theory, what we say is that we have the fact that the waves have different propagation direction. We say that it's the reason why the wave, we can have some threshold effect. So you have the primary wave. You have some interaction region where the 3 waves interact together and interact together. And you have the 2 secondary waves which has different group velocity. So what we say is that the waves can exchange energy as long as they stay in the same region. So we have 2 different type scales, the growth timescales of the instability and a timescale which is related to the fact that the waves is advected away from the interaction region. This is what we have introduced, these two timescales. So we use also the amplitude equation we have done before, but like using an energy balance. And we say that we have the coefficient of interaction that gives some energy to the first secondary wave, also the dissipation, and another term which is related to the dissipation, explaining the fact that the wave is going away the interaction region. And in fact, if using this simple energy balance, we can obtain two new equations with the new terms, which which is linked to the finite size of the wave beam. In this case, we can calculate also the growth rate with which is the growth rate with no. This is a first approximation, the growth rate for the plane wave, and this is the effect of the finite size of the wave beam. And what we can observe is that for small, so this is the growth rate sigma, not small sigma, as a function of the finite size, you can see that you have different behavior of the growth rate as a function of the width of the tank, of the wave beam. And you can see that you can obtain that for 3 wavelengths, the maximum growth rate is now given in the external branches of the resonance location. You can have some threshold due to the finite size of the tank, meaning that the wave, at least when the wave is created, is ejected away the interaction region, so it has no time to really grow in the tank, or maybe it grows so the amplitude is so small that it's not possible to see it experimentally. And the thing is that if you increase strongly the width, so this was not possible to do it experimentally, so what we have done it numerically, and we observe another wave which is in the other direction. And I will stop here for this one.
Because there is a coffee break out, and we have to be in at 11:15
Okay.
at the bar. If there's just one question maybe, or
Yes, in fact, okay. Okay, I will answer.
fixed, or we start reaching here, so no schedule.
Yes, but not 2 hours, I guess. Yes, I should. So I should start with an answer, but I don't really have the answer. um,
Yes. Why you have an effect on the growth rate from the group velocity? I will just say that it will affect the growth. So it will grow for a small amount of time. So the amplitude of the wave will reach not a sufficiently large amplitude to be seen. That's all.
Yes. Yes, in fact, it's what so it's what I said as the intuition, so that the wave goes away the interaction region fast, and the amplitude doesn't grow enough. So in the so why it we interpret this. So I think probably we made many approximations to write this, and we assume no spatial dependence. So I think it arrives in the growth rate. I'm not sure I have the right answer to this question. So the group velocity arrive in the problem using the advection term. That's clear. The way we did it, I understand why it appears in this. So in this equation, we made a balance on a domain and the way, and that's something we say, and maybe it's not correct, that energy in the domain grows, but part of energy is ejected, and we use this proportionality coefficient, and the time for ejection is related to the group velocity, and we said that it has already grown, and it continued to grow from the energy that was previously. So what you said is that it will change the finite E, the finite energy, and it should not be proportional to E1. I think that's the way I can understand the point. I'm not sure I have the answer, the complete answer. With the experiment, it fits well. So that's probably the way we model the problem is not completely. We make a lot of approximation in this model, but it was to capture the effect of the finite size. So that's, okay. So if I come back to this, what I have said, so I will just come back in this, and so this, I have already discussed this. So this is the effect of finite size, and you can see that it tunes both the threshold, so by having large plane wave, the threshold, you have no threshold, and if you reduce the size, you don't have enough time to have enough energy exchange, and therefore there is no instability. The secondary wave cannot be seen in experiments. And you have also selection criteria, because secondary waves are not advected at the same time, and therefore there is no, it will change a bit the interaction coefficient. If the wave is ejecting fast, it will not interact and will not see these waves. And it's what happened in the in these two waves here. If the width is very small, we don't see it. And if the width of the wave beam is large, this was done in numerical simulation by Michele Dolce Long-time, we observe some instability here corresponding to this two growth rate that was not observed in experiments with 3 wavelengths. So clearly the finite size is affected. So that's one of the limitations we have observed for the use of plane wave theory. So just a few words, but that's a theoretical approach. I will just give mention to this paper. We made an approach, a very basic approach with balance of energy. It was done theoretically by Karimi and Aquilas in a nearly inviscid limit using a development with slow time and small beam amplitude, and they used the expansion of the solution. And they made the calculation, and they observed, they derived the equation using this approximation and this multi-scale analysis. So you have the same coefficient with the energy, the group velocity, and the width of the wave beam, which appears here, the viscosity, and you have the interaction coefficient in this case. So I will not comment on how they did all the calculation, but they did this multi-scale analysis, and they observed similar results as what you have done with finite width in this paper. And the key parameter is clearly the group velocity that changes, and it's that's why we simplify in the time of advection. So this is many things that we have done in 2D experiments. And one question that we can address experimentally, is it really 2D? That's, we have done the experiments, we have done the theory in 2D. So we look at, so the tank, if we come back to the experiments, the tank has some width, which is 17 centimeter. It's small compared to all the other size, but it doesn't mean that you have no motion in the transverse, in the direction perpendicular to the plate.
Can you say how it compares to the wavelengths?
The wavelength, it's 3 centimeters, so it's much larger than the wavelength. It's much larger than the wavelength, and you have 3 wavelengths, so it has more or less the same size as the width of the wave beam. So it's, but the plate of the forcing, it's around also, it's 16 centimeter. You have 0.5 millimeter on each side. So the forcing is almost 2D, except very near the wall, because it was impossible to force near this size.
For the dissipation, would you expect that the effect of the vertical boundary is of the same size or smaller than the volumic viscosity? Because I guess it would not appear exactly the same way in the model. I guess it would not be a second order derivative.
So it really depends on the. It really depends on the wavelength of the tank of the wavelength of the beam. So I made a small estimation of the bulk dissipation, which is related to this, and the boundary dissipation. In this case, so I expect that you have, so just first, this is an experimental result. Y is this direction, and this is experimental points, and this is some model of the shape of the wave beam that was done in this paper with low mass, and they solved the boundary limit with in this geometry. So you're almost flat over the whole width, and you have just a viscous layer near the wall, which is of the order of 1 millimeter. And if you do, so the calculation, the boundary dissipation is related to this boundary layer compared to the width of the tank, and with this coefficient. And if you compare both bulk dissipation and boundary dissipation for 3 centimeter wavelengths, you have the order of 2. So the dissipation in the bulk and the dissipation on the side is very similar. And the problem is that we have observed in some experiments, if we increase the wavelengths, this will decrease, but not this term, and the boundary dissipation will be clearly dominant in the problem, and it should be taken into account in the model.
Can you write a 2D model with a dissipation which accounts for this boundary dissipation?
Yes, we can write it with a term which is minus alpha v.
Oh, just a friction.
Just a friction. We could change a bit the value of alpha with the dependence of omega, but it's like a friction. And it doesn't change. And in fact, what changed in the problem, in the dissipation equation, it changed almost. In this equation, it will not change that much. It will reduce the value of the growth rate. So if I have the growth rate like that, it will shift the growth rate like that. But clearly, that's something that may be important in the 2D. In these points, here I have a black circle. You have a case where the wave is linear, no instability. You have weak instability or strong instability, and in any case, you have the same behavior. So with the instability, it stays 2D. And I know that you have talked about boundary layers tomorrow. We also observe some streaming due to boundary layers in this tank, and some mean flow generated due to the boundary layers. I will not discuss this, but that's. But clearly, that's one effect that should be taken into account in the problem, and usually it's not taken into account in the model. Another thing I want to discuss about 2D versus 3D is a comparison between internal wave and inertial wave. I will just, so for the equation have some similarities, especially on the dispersion relation, which is in one case related to the buoyancy. For inertial wave, you have something which is related to the Coriolis parameter. The thing that for plane wave, for internal wave, you have a 2D structure, which is not the case for inertial wave. You have an inherent 3D structure for inertial wave with some anticyclonic motion, which is the fact if you have one Vx, you generate automatically a Vy, which is related to F. using this, the result from this paper, you can derive the same way some amplitude equation, the same way we have done for internal wave. We just change a bit the parameter, and the factor will be modified, but you have a similar structure of the wave amplitude equation with an interaction coefficient which looks similar to the interaction coefficient we have done for internal wave. So we have the same amplitude equation for TIA, similar interaction coefficient, and the growth rate has exactly the same shape. What can change is, and in this case, so in this paper they have done numerical theoretical development and experimental study. So they use the same wave generator we have used in Lyon. So it was done in Orsay, and you generate wave beam, which is like that, with a group velocity and a phase velocity, and it's really the same as internal wave, but the motion of the wave is this u, which is anticyclonic. Looking at this, you also observed some TRI, triadic resonance instability for inertial wave, and you can have, so you can calculate again the same resonance localization for the instability, for the triadic resonance. You can look at, we can measure the value of K1, K2, and K0. And you observe that you have also resonance condition satisfied in the spatial resonance in K, and you are in the dispersion relation. You are close to the growth rate of plane waves. So it's really some similarity. The differences you can observe in this are the frequency spectrum. So this is for internal wave, the case I have shown before. You have the omega naught, omega 1. Omega naught is here, omega 1 and omega 2. And in this case, you have the forcing here, and you can see two bumps corresponding to the secondary frequencies. So we still have some temporal resonance condition. The difference is that for inertial wave, the shape of the bump are wider than for internal waves. That's the results we have observed from all the inertial wave experiments, that for plane wave, you're very localized at the single frequencies, and for inertial waves, the spectrum is a bit broader than for internal wave. The explanation we have, but we don't have completely, we don't have complete evidence, is that it's probably, could be due to the 3D structure of inertial wave compared to internal wave. But that's some intuition. I don't have complete proof of this. Yes.
If you look at the same locus curve that you had previously, actually it should be a bit different because you have an additional degree of freedom, right?
Yes, with
so
the.
It's a surface.
Oui.
You have so for the internal waves that you mentioned previously, you had only two components of the wave vector.
Yes.
Now you have three, right?
Yes.
And you have, so you have, say, more possibilities somehow to.
Yes.
And so it's not clear to me why you would get only one maximum or.
So in fact, okay, it was 5 slides later, But no problem. What you will see. So in this experiment, the experiment was designed so the tank was a bit wider, but in this case, the localization was, the theory was made in 2D. We assume that ky is strictly 0, and we calculate the maximum growth rate. And we found that it corresponds to experiments. So therefore, we didn't look further. Few experiments, a few years later, they have done new experiments, and they have seen, I can go a bit. No problem. Yes. And so I think that's, yes, they have done new experiments on the platform. So it was done in 2020, still in Saclay with Pierre-Philippe Cortet. Similar wave generator. The width a bit wider than the tank, but larger tank compared to internal wave experiments. So 3D effect are possible. They observe a time frequency evolution as a function of the forcing. Small forcing only, small forcing is this one, the forcing frequency. At no forcing, you have the noise of the table, rotating table. And if you increase the forcing, you can start to see some bumps corresponding to secondary waves. But now you still have the temporal resonance condition that is satisfied. But if you look now, so this is the primary wave, and this is the two secondary waves that are generated. So they measure the experimental value of K1 and K2, and if you plot them in the plane with Ky equal to 0, you're far away to the resonance curve. So you have this in this plane. So for Kx and Kz, you have the spatial resonance, but you are not in the resonance. So it means that if you assume Ky is equal to 0, you don't satisfy the dispersion relation. Yes, and it's what they have done. In fact, so they have no evidence, no measurements in a plane. So they have no measurements in the y direction. So they use the vertical measurement, and they say that okay, they use the dispersion relation, and they use the difference between the dispersion relation to calculate a value of Ky. In this case, they obtain that the value of Ky, if you put this value, you are in the dispersion curve, which corresponds to this point here, in the resonance curve. And this is done, so you have a surface, and they change the plane with K1 for different Ky, and this is just a plane view for different value of Ky or Kx. And what they observe is that if they impose this value of Ky, they retrieve a case where you have resonance, spatial resonance condition, temporal resonance condition, and you are in the dispersion relation. And to complete their study, they have already done again the calculation for the growth rate, including possible value of Ky, and they let Ky free. You have also the spatial resonance condition Ky1 equal Ky minus Ky2. You calculate this term C1, C2, which is slightly modified. This is by this angle that the Ky values is given by this angle here. And if you calculate the growth rate in the Kx, Ky KY plane, the growth rate is maximum at two locations, symmetric, but that's logic that you are symmetric plus or minus, corresponding to a value of KY that is not 0. And the maximum growth rate, so you have a single maximum growth rate at a value of KY that is different than 0. So you have 3D behavior of inertial wave. And under agreement of the grade, they estimate the growth rate. You are here. You measure with KXY. The measurement of KX and KY you have in experiment, you're close to this maximum growth rate here. So.
Can you explain why you don't see this if the width is too small? Because this KY is too small to be considered.
I think it's within the error bars. So if KY is small, so if KY is small, probably you don't see it's in the errors of the measurements, or you're close to the localization, but you don't. So I think that's. See, the only criticism I have on this paper is that they should see something in they should see some velocity in the y direction, but they didn't show any view where you can see this. So they interpret their difference with this. It seems to be correct, but they don't have any experimental. Yes.
But, okay, I'm a bit lost, but this is.
So this experiment is talking about inertial waves, that you're saying we have 3D effects.
Yes.
Okay, just to recap. So, but also this experiment, if I remember correctly, has a very, very different geometry. Isn't that one in the sphere? No, maybe
No.
Oh, okay. So it's the same geometry.
It's I think it's a cylindrical tank.
Yeah.
To avoid any corner effect because you're in a rotating tank.
Yes.
But you have even I'm not sure. But you have the same wave maker that we have in Lyon.
Yeah.
We use this. They use a wider wave maker, but they start with a wave which has a width very similar wave that was done in Lyon. So they have done other experiments with other wave maker, but this is really.
Okay, but my question is, like, why don't you account for any reflection? It doesn't matter. Like,
in fact, so in the field of view, so you have a reflection, but they are attenuated enough, and you don't see it. And the secondary waves grows before the reflected wave or back to the tank. That's usually the difference between modes that we have used a lot in Grenoble or in Lyon. For plane wave, the dissipation, the tanks are long enough so that the reflected wave does not appear. And it seems, so I have done quickly the calculation, but I'm sure I have made many small mistakes in the calculation. But for internal waves, the maximum growth rate is for ky equals 0. So I think that's different. And it's because you don't have this effect of the 3D structure for internal waves, and you have it for inertial wave, and you have this difference between the 3D behavior between the two. So that's. I think I should do again the calculation to be sure that it's really the case. Okay. So I will come back a few slides before. Okay, so I wanted to point out inertial wave compared to internal waves, and to have this structure that are present 3D versus 2D. That is important for the instability and therefore for any phenomena that are after. Okay, I will continue discussing about rotation. and I will put together rotation and stratification to see what's in the problem. So, okay, I have done the experiment. So what we have done is we have taken our tank we have used for the stratified case. So same width, 17 centimeter, and all the system is in rotation. And we wanted to look at is the Coriolis effect important? What will it change in the results? Okay, so that's easy. So now, if you look at the dispersion relation, is slightly modified. You have to take into account both stratification and rotation, and you have this combination. But for one frequency gives one angle of propagation. So that's similar. So we have measured the dispersion relation for many cases, and clearly we can satisfy. Experimentally, what we did, we start to fill the tank, the stratification. Then we put the tank in rotation. We wait 4 or 5 hours that all the fluid is in solid body rotation, and then we do the experiments. I think in Grenoble it was done, you start the rotation and you fill the tank after. In our lab it was easy to do it in this way. But the stratification is not modified when you put it in rotation if you do it slowly. The thing is that even if the tank is small, in rotation you should have a transverse velocity, but what we have done is small values of f, so Vy is not really affected. So it exists, but the wave we observed, if we are still of internal wave, so f small compared to n, we are not affected by the boundaries and the presence of a transverse velocity. So we can still see waves that are they have their displacement, because the y displacement is very small compared to the tank width. Okay, so the first thing we wanted to see is that, okay, we start, we? Yes, yes, we put our tank directly to the rotating table, so it's still a parallelepiped. In this experiment, we don't see any effects because of parallelepipedic tank, but it may have in the corner, but we are far from the corner. Okay, so to look at the effect of Coriolis on the instability, we look at the value of omega naught over n and the value of f over n. So in this case, we are stable. So we start with a stable case with no triadic resonance instability. And if we change, so if we keep constant the value of omega naught, we keep constant the amplitude, we change the value of f, and we start to see some instability if f increases. So f has clearly an effect on the threshold, and okay, the effect is more pronounced for larger omega naught, which was already what we observed for with no rotation. Larger omega naught helps to see this instability. Okay, so the first question was, how can we understand this behavior? And so we did again, so the same calculation. So first of all, the localization of the triadic is modified by the presence of the rotation. You change the dispersion relation, you change this shape. So you start from the gray line here with no rotation, and the black line is the one that is observed for small rotation. The change is that it's not possible to have values of omega smaller than f. So you have some values of k that remove some value of k. And so this is the experimental time frequency diagram. We still see the two secondary waves. We still have the temporal resonance condition. And for the wave vector is also the same. We have the spatial resonance condition that is satisfied. And we are on the resonance localization. So that's still valid in this case. So what we have done, so in this plot, I have calculated a growth rate, so we can also do the same calculation, so I will not do it again. What we have done is that we still have used the stream function, but we have added a value of ui. We have assumed that we are still in 2D case, because we are dominated by the stratification. And we can calculate the amplitude equation, and basically is the same as the previous amplitude equation. We have a new term due to the rotation for the viscosity, and we have a modification here of the interaction coefficient due to the rotation. So if you calculate, you have the growth rate. You still have the same value. I have just, in this case, to simplify the calculation, I have assumed I have very small viscosity. Well, we can do the calculation for any kind of viscosity. And now we have an amplitude threshold due to the rotation. This was not the case for internal waves, because we can assume that K1 is close to K0, and this leads to a value of omega, which is almost 0. And this is not possible with rotation. So the fact that you have the rotation, a threshold is imposed in amplitude. And I calculated the amplitude of the threshold this threshold as a function of f. So this is an asymptote going to 0 here, and this increase. And in this case, you're stable. In this case, you're unstable. So you introduce a threshold due to the rotation and due to the fact that the dispersion relation is between f, omega is between f and n. The other things is the finite size effect. So the group velocity will also depend on f, and so the fact that the rotation changes the angle of the group velocity, we have some values where the group velocity is going to 0, and so the secondary waves can stay in the interaction region and can so develop more or having strong, larger amplitude. Okay, so altogether, I will not do it. If you look at still with the finite size effect, at the ratio between two time scales, so tau sigma is the viscous time scale due to only viscosity. This is the time scale due to the finite size effect with the group velocity. What you see is that this ratio decreases and have some value. So what it means is that you have an existence of an optimum range around a particular value of the rotation rate. It's resulting of the group velocity. And so that shows that the finite size effect does not have
is not have the same importance for all rotation rate. And in this regime, this has less importance, and you should see more instability than with no rotation. And I have the same with, so it's inviscid, but it's the viscosity is going to 0. And you can see that you have also a single point near omega naught over omega naught corresponding to PSI. Okay, so we have done experimentally an instability diagram plotting the function omega naught over n as a function of f over n. So the cross are no observed instabilities, and the circle are instabilities. What you can see is that at small value of f over n, you have more or less the same behavior and the same threshold that does not depend on f. And some point, this threshold in omega naught is reduced. Okay. So we have tried to model these results using all the ingredients I have put together. The first one is that first there is a forbidden zone for TRI, meaning that omega naught should be larger than 2f. That's to have both omega 1 and omega 2 larger than f. The second one, I used a simple model using the comparison of time scales. What I did is so the model means that you impose a threshold in omega naught, and you look at the variation of the threshold in omega naught using this comparison of two time scales. Using this model, we have this line and resulting to the finite size effect and the effect of the rotation rate on the group velocity. And it's a similar behavior. You have a region where you're more prone to the instability than with no rotation, which is in this case. And we have a very good agreement with our experimental data, except close to this line where you have discrepancies, but that's the main result is the first part where you have seen our explanation with the finite size, with the group velocity that is consistent with the experimental results. In the same group, yes?
Is there a simple physical explanation for the stabilization when the rotation gets stronger?
In this?
I mean the region on the right.
Here, it means that you cannot have, you have small region of omega, for omega 1 and omega 2, where you can be propagative. So in fact, this this one. In fact, if f is increased, it goes above and above, so you are to larger wave vector, so smaller wavelengths, and this is due to viscosity is less good for the instability. So the explanation is really you have less possibilities of omega that are compatible to the. And just in this, in the group of Aquilas, they have done the calculation with rotation using this same modelization that they have done for finite size effect, and they also observe similar behavior that we have done, that we have observed in experiment. Okay, I have talked many things about
I want to just to continue because I have one point. I don't understand what happened, so that's. Okay. So in this plot, I have shown the evolution of the time the frequency spectrum as a function of f. For this, you don't care about the quantitative value. I have just shifted all the spectrum vertically to see the difference. So you increase f, you have the same value of omega, or almost the same value of omega. You observe some TRI for small value of f, so this is consistent. The rate point is the value of f over n. And until this point, things are going well. You're consistent. You have 2 peaks or more peaks at some particular values of f over n. And then if you continue to increase, you start to see that you still have a region where you have 2 frequencies, so 2 secondary waves, but one of the secondary waves is non-propagative. So one is below f over n. So the omega is smaller than f and smaller than n. So you don't satisfy the dispersion relation that tells you that omega is between f and n. So that's. It's not. It's not a wave. Can be an evanescent wave.
I don't have an explanation, but we observe something very similar with waves that are long waves over n. So on the other side of the spectrum.
Yes.
So, yeah.
Yes, that's. Okay.
Very stupid question.
Hmm?
Why should it satisfy?
In fact, in all this, that's so. In the theory, if we compare, when we do the theory, we impose that the 3 secondary waves satisfy both the resonance conditions and the dispersion relations for the 3 waves. Yes. But for the if one secondary wave is not in the dispersion relation, it's not clear its amplitude can grow. It can grow if 2 waves exist in the same region. But clearly, what we have observed for no rotation is that you have one wave. So in this case, you start with a primary wave. You have a secondary wave that's going that direction and is out of the primary where the primary wave is, and the secondary wave is in that direction and also out of the primary wave. If you have not a wave but a frequency smaller than f and n, you have some energy, but it can exist. It can exist in this region. It's interaction, and you can. It's the nonlinear terms give rise to some amplitude, you have some energy at these frequencies. That's.
The background stratification or the background rotation has not been modified by the waves themselves, or
No.
it's negligible?
It's negligible. That was our first guess. But just to show how it looks like, so it looks like this. So this is one case where omega 2 is smaller than f. So you start with a wave, like that. You have a plane wave, you have this primary wave, which is K naught. You have the first secondary wave, which is between F and N, which is K1, so which has this shape. And you have, you filter at omega 2, and you have a structure which looks like that, where you can also define a K2. So we have a wave. That's why I say it's something I wanted to show it because it's not clear for me what happens, but clearly, so we have a wave. The thing is that what we measure the value of K1, and we estimated the value of K1 with the dispersion relation, and they are not in agreement. So K1 with the dispersion relation is this arrow, and K1 measured experimentally is slightly tilted. So that's...
I get the same for K2. You would say that the frequency was below
F and N.
If you measure the frequency from this kind, which is related to the angle,
Yes.
it's above.
In fact, with the dispersion relation, I was not able to put an angle because omega 2 is smaller than F and N.
No, but here you have
Yes.
an angle between
Yes.
the Kx and the Kz.
Yes.
So you can define the dispersion relation. So you can have an angle, and so you have the frequency.
Yes. But the frequency will be smaller, will be larger than F, and is, yes.
That's what you said, right?
Hmm?
You said that it doesn't match the
No.
dispersion relation. You have a K2 that you can measure, you have an omega 2 that you can measure.
Yeah. We have a K1 plus K2 equal K naught. We measure it. We have omega. We have the temporal resonance condition. We have the spatial resonance condition. We don't have the dispersion relation, but I have no way. I don't know how we can predict the value of K1 and K2 we measured in these experiments. And why?
This is not filtered at omega 2.
This one? Yes, it's filtered at omega 2.
But omega 2 is below.
F and N. Yes. Yes, I wanted to show this. Just the first thing is I think I filtered many times because I was sure I made mistakes on the filtering, but we did it for all these cases here, and we always observed a value of K1 and a value of K2. Yes?
Yeah, for surface gravity waves, there is a frequency, a nonlinear frequency correction, which you add to the linear frequency, right? I'm asking if in the internal wave, do you have a nonlinear frequency correction or not?
I think for plane wave, no.
Okay.
I think one thing that may be possible in this experiment is that you may have an influence of the plane wave on the fact that you have like some Doppler effect due to the presence of the plane wave, of the primary wave. That can switch a bit the situation. That's maybe one explanation.
Okay.
The same.
This is localized near the top, right?
Yes.
So there are surface waves which are below F.
That's also, yes? Hmm.
But there are also bound waves, so I think it's related to that. I mean, there are these bound waves which satisfy the triadic resonance condition, but they are not resonant, so they are not.
Yes. The thing is that it's what we think at the beginning. The thing that these two results in K1 and K2 were strange for us is that, okay, if we have bond wave, so how K2 and K1 are defined in this case of bond wave? How can we predict this?
They are not on the resonant
No. You have the spatial resonance condition, but why these values of K1 and that's yes, yeah, but maybe it's really localized near the surface, so maybe there is some effect close. Maybe also there is some close effect close to the wave maker, and maybe it's just an artifact near the wave maker. So that's also a possibility. But I think, close to the wave maker, it will not change the value of f. So, but that's one result we have. We don't understand, and I think I will not. And to complete, we have measured these values of K1, and the dispersion relation and the disagreement between the two increases if you go further in f over n. So that's for the experiments that are here. Okay. I think I have. I will show one last result. And so I think it's in this with 3D. And the last result, all I have discussed is the beginning of the instability. So what is the maximum growth rate? Which way? The question is the long-time evolution. So there are many works on multiple cascade of waves. I just don't want to talk about this. I want to talk about experiments done by Catherine Grayson in Cambridge, and she looks with she looks at the long-time evolution of the triadic instability of these three waves interaction. So they use their wave maker, so the magic carpet experiment. And they have a larger tank than in Lyon, so no reflection, no effect of the reflected waves. And what they observe the same results as we have done for internal wave. So in this case, internal wave, stratification, no rotation. They also observe some TRI, which satisfy all the conditions I've already discussed. What they observe is the long time behavior of the frequencies. And what you can see, so this is the experiments we have done, and the experiment they have performed in Cambridge. And you can see that you start with a wave that is that is fixed, imposed by the wave maker, and the secondary waves oscillates along the time. And the question they ask is, why do they observe this oscillation? So if you solve the problem, you have one frequency that appears. Why do you have some oscillations? One result they observe is that the temporal resonance condition is valid at all time. So you can see that if the frequency increases, the second one decreases. So it's valid at all time. But if they observe some snapshots at different time, they observe that the localization is not the same. So different time in the regime. At some times, the secondary waves is in this region. Another time is more below. Then you have one here, one here. So clearly, you have some spatial effect in the resonance condition. You have some spatial effect on the long evolution behavior of the secondary waves. And so, the interpretation is that for finite beam, the spatio-temporal position of the triad is really important. So in all the theory, I have studied only the temporal evolution of the secondary waves, their interpretation is that you have to take into account the spatial evolution also of the two waves. And what they have done to do it, and they have done again the same analysis we have done for TI, but now they have done the multi-scale analysis, including time, but also space, and saying that you have a small evolution of the primary wave, a small evolution also of the secondary wave, and they do all the calculation, taking into account both the spatial derivative and the temporal derivative. And they build their solution, their evolution equation like that. So they have two, they have do a numerical analysis using two evolution, one linear taken into account a group velocity, and one nonlinear, which is similar to what we have done in time. So they combine both in a numerical results. And what they observe, I think that's the last one, they observe some oscillations that are close to numeric, that they observe experimentally. And there's still some discussion on how we can interpret it. But they use this, so it's a small modification of the amplitude equation we have used, taken into account, to take into account the spatial effect of the secondary waves on the primary waves. And so therefore the secondary wave does not appear in the same position, and this will tune a bit the frequency that appears in the domain over time. That's the physical interpretation of these results. Okay, and I think I will end with this, because I have done many things on TRI and all the small modifications that have been performed, and we still have some questions to understand all this behavior. Yes.
Are there some questions? Are there some questions? There are some questions.
So in usual geometric optics, if I remember well, you have this idea of corrections introducing slower time scale and
Yes.
and larger space scales. So that's really what they are doing, this multi-scale expansion you are referring to?
Yes, in fact, it's the same. Yes, the multi-scale, you use the same ideas, that you have a small evolution of the secondary waves, and the multi-scale analysis is done, yes, exactly the same. In fact, we use the same equation from the beginning that we have done. In our case, we have just used time evolution, and we have done a multi-scale analysis on time, and we have assumed that all the spatial derivative of lambda, or kx or kz, and now they add this evolution in space to interpret the long time behavior.
Maybe the equations that you show that give an answer to my first question for concerning the group velocity effect.
Mm-hmm.
I guess it will introduce a kind of time shift or,
Yes.
or detuning effects that will affect the growth rate.
Yes.
And probably to take into account, you have to do a multiple scale analysis to introduce and to see this effect.
Yes. Okay.
Okay, then, thanks.
Yes. Okay, so welcome to this afternoon session, and the first talk will be given by Costanza Rodda. She's got two good news last year, a baby that we have seen early, and a position at Imperial College in England. So.
Thank you. Okay, so thank you very much for inviting me to present my research in this fantastic venue. Also, it's the first time I'm in Rome, and probably I'm the only Italian who has never been to Rome before, so thanks. Yeah, so my talk today, as the title says, is about baroclinic instability. I thought it would be a good fit for the meeting topic. And I'm going to focus on laboratory experiments, which is what I do. In particular, this is work that I've done during my PhD in Germany some time ago. Okay, so let me just say a few words about baroclinic instability. Well, it comes from the word barocline, which bar is pressure and then slope. So it's an instability which arises from sloped pressure contour. Now, I'm quoting Wallis, who is a prominent figure in this field. And he says that baroclinic instability, because it occurs in stably stratified rotating fluids, it's ubiquitous in the Earth, atmosphere, and ocean, and probably also on other planets. So it gives rise to weather, and it's perhaps, well, the form of hydrodynamic instability that affects us the most. And that certainly we talk about the most. That's because he's British, probably. In Italy, we have good weather, so we don't talk so much about weather. Anyways, jokes aside, it's an important instability in the geophysical context. And I will give you a physical picture of it, but let me start setting the scene by reminding you of the equation we are considering. So these are the Boussinesq's equations. We have seen them before. Sylvain did a very good explanation, so I'm not going to go into the details. I'm just for the symbols we are using. So we have U, bold U, which is our velocity vector, then F is the Coriolis parameter, rho is our density, and B is our buoyancy. So these are the three equations governing the fluids. Now, for oceans and atmosphere, we can do a dimensional analysis, and if we look at the dominant terms, what we find is that what matters the most is this geostrophic balance, which you can see here. So it gives you a relation between the vector product between the Coriolis force and the velocity with the horizontal derivative of the pressure. And then there is another balance that comes into play, which is the hydrostatic balance. So we have buoyancy, which is balanced by the pressure gradient along Z. Now, why am I talking about this? Because you can easily derive from these two balances one equation, which is the thermal wind balance. And now I'm taking just one component, okay? Before we have, of course, also the other component coming from the equations I showed before. And the thermal wind balance balances the vertical velocity derivative multiplied by the Coriolis term with a variation of density in the y direction. Now, if I want so this gives you an equilibrium state, okay? And the physical picture that we can see related to this wind balance is the following. So we have, I'm taking a 2D domain, we have Z, the vertical direction, and then we have, you can consider this in the Earth equator to pole, okay? And what we have is that the density changes both with height and northwise. So we have these slanted density contours, right? So is this configuration stable? Yes, it is, provided that we have a shear of the wind, okay, in the vertical direction. So this is perpendicular to the plane, and we have wind changing with the direction. Okay, so this is our equilibrium state. And now to consider an instability, we can ask ourselves, is this stable to perturbations? And the answer is no, but we need to take a particular perturbation. So imagine two cases. We have a fluid particle A, and we exchange it vertically with C. Okay? This is a stable configuration because we will have a lighter fluid, a denser fluid particle in a lighter fluid, so we'll just go back and forth, oscillate, all stable. However, if we exchange A with B, then we have a denser fluid, a lighter fluid in a denser fluid, okay? And this is not stable anymore, so the two particles will grow further apart. And moreover, the gravity center of the system has lowered. And this gives rise conversion from potential energy to kinetic energy. So this is the physical picture of our baroclinic instability. Now, that was about what I wanted to say about the baroclinic theory. And I'm going to switch now and jump into the experiment. So how can we represent... but before I do that, I want to say that this was quite a crucial work that was developed in the 50s. So there were two main people working on instability criteria and models. So these were Edie and Charney. They developed two different models. But together with these models, and you have to think that in the 50s we didn't have all the satellite images and everything, so we didn't know exactly what was happening in the atmosphere. So these were models for the circulation in the atmosphere. But at the same time, someone was doing laboratory experiment work to verify these theories. And the experiment is this one, and I'm going to show you some more pictures, but I want to explain the analogy. So we have a tank which is rotating, and this tank is divided into 3 concentric cylinders. So this is a vertical cut of it, and we fill it with water, and we have warm water in the outer cylinder, cold water in the inner cylinder. So we have, as you can see, the 2 ingredients that we were talking about before. So we have meridional temperature differences, okay, and then we have rotation, and of course we have gravity. Okay, so these are the key phenomena for the baroclinic instability as we have seen before. And you can quite nicely see that this is a laboratory model of our atmosphere. So, of course, there are a lot of things that we neglect. We don't have curvature, we don't have sea, land contrast, but these 3 ingredients are the only key ingredients to develop the circulation of the atmosphere. Now, the first person who looked at, and actually the inventor of this experiment is Hyde, so in the 50s. This is a historical picture of the experimental setup that he had. And he did very important work, first verifying these theories, and then really looking at these patterns that develop. And you can see nicely that these wavy patterns are similar to the mid-latitude circulation, which I'm going to talk about in a second. Okay, so I'm going to show you how this baroclinic wave develops in the laboratory experiment. So what we do is we set, as you were saying, Sylvain, before, so we set the temperature difference beforehand. We let it reach a constant temperature difference, and then we start rotating the experiment, and then we wait several hours that everything is in equilibrium, and then we see what happens and what develops in the lab. And this is a top figure, a figure from the top. This is a co-rotating. Yeah. Yeah, okay, I can repeat. So how can I maintain the temperature difference? Okay, so basically what we have, okay, so in the first experiment, they put ice, and they just had room temperature in the outer, but that was not very well maintained because the outer temperature is difficult to control. But because we have 2 baths, we have a cooler and a heater connected. So we maintain the heat, the temperature constant. We can regulate them mechanically with the cooler and heater. Does that answer? Yeah. Okay. Yeah. And so what happens, okay, it will hopefully start again. So this is a top view of the experiment. We have a camera, which is an infrared camera, so it measures the temperature. And we can see from the beginning of the rotation and then so you see this is an axisymmetric flow at the beginning. Okay, so let me describe the tank. Okay, so you can see that actually this is accelerated 30 times. So quite quickly though, at one point, we have the inset of the instability, and you can see that these cold tongues from the inside develop towards the outside, and then now you can see that it shapes as a more regular wave, okay? And this wave is propagating, it's prograde, okay? So it travels faster. You can see now that it's developing, it's quite stable. Yeah, so this, we took this, we had a small experiment, so it's about 30 centimeters diameter. It's quite nice because you can have the whole view. Yeah.
Why do you get two vortices?
Oh, that depends on the parameters that you set. You can get many more. There is a geometrical constraint, so the width gives you the minimum and the maximum. You can see it's, but then according to the temperature and the rotation, you have a parameter space and can go from to, it depends on, again, on the geometry, but it can have several. And actually, I haven't studied it myself, but in these 50 plus years that this experiment has been used, many studies have been done on, for example, bifurcation. So you have the same initial conditions, but then there are sometimes wave number 3 and wave number 4 forming. There is two stable modes that could arise. So this is really an interesting system. It's rich in literature. Okay, this was a bit of history, but now let me talk about what I have done with a large group of technicians and other scientists. So now about the size. We have built a much larger tank. This is about 1.5 meters large. It's one of the largest for these differential temperature experiments. It's quite challenging, let me tell you. First of all, because you can't see the whole tank measuring, and also because maintaining a high, large temperature difference in such a big tank is a very difficult engineering problem. Why did we build this tank? Well, one of the shortcomings of this tabletop size tank is that it's not very atmospheric-like. So in the atmosphere is a very thin layer. But this tank has a large depth and a very narrow gap. So this is quite different from the atmosphere. And then what we wanted to do is actually to have this aspect ratio not as good as the atmosphere, but here we have more or less 4 or 5 centimeters of water, so a very thin layer into 1.5 meters tank. Yeah. And okay, so with respect to the historical experiments, the advance of science and computation and measurement techniques allows us now not to have just point measurements of temperature, which were done in the past, but to have the full 2D velocity field. So we did particle image velocimetry, which is this technique where you seed the fluid with particles, neutrally buoyant particles, then you illuminate them with a laser, and you record everything with a camera. And, well, okay, Sylvain already talked about this technique, but let me just remind you how this works. So to process the data, you basically take an interrogation window with some particles, and then you track the pattern of these particles, so you don't track them singularly, and you see where they moved with the recognition pattern software. Okay, and then you do some calibration to transform these pixels coordinates into physical coordinates, and what you get is the velocity field onto a Cartesian grid. Okay, so I told you that we have new measurement techniques and a new tank. So what did we want to study? So what we want to study is the interaction between baroclinic instability and our internal gravity waves. So one thing is that in the past, these gravity waves were even scrapped out of the meteorological and climate models. They were seen as noise. But actually, those are really important, especially in the atmospheric motions, because they interact with the mean flow. So not only wave-wave interactions, but we have an important part of wave-mean flow interactions. And so this interaction can drastically change the mean flow. And why is this important? Because these gravity waves are small scales. And so still nowadays, even though we have good resolution in climate and weather forecast models, they are not fully resolved. So they need to be parametrized. And just because I have nice videos, let me show you. So nowadays, this baroclinic instability is quite clear. We have very nice representations of this mid-latitude jet, as I was showing you before. This is a nice NASA model. And the gravity waves, they come from many sources, but part of them, which are these blue and red contours here, as you can see, they run along these green streamlines, which are the streamlines of the baroclinic jet. And now, this is an equivalent figure of what we have seen this morning from for the atmosphere. So gravity waves are generated by very different sources. So we have topographic generation at the ground, then we have convective generation at higher up, and then we have secondary generation and spontaneous imbalance. Now, one thing is when you observe the waves and you measure them in the atmosphere, it's very difficult to know where they come from. Because you measure, the fact that, for example, you measure them along the jet doesn't mean that they are created at the jet. They might have been generated somewhere else and then propagate to the jet. And so one very important question is, how are these waves that we observe on the jet generated? And this is what we want to answer with our experiment. Okay, so first thing, I want to stress this because before we have seen that in the experiments, the waves were forced. We don't force gravity waves in any way. So what we we have forced the baroclinic jet. Okay, and so we don't know at which frequency these waves are going to show up, if they are going to show up, because that was not sure. So after a lot of research and a lot of experiments, we finally saw the waves. So it might be trivial for many of you, but for us, just seeing the waves was a great result. So I'm not going to drive you through the process of finding these waves, but basically what we have seen, and here is just a summary of that, we have here the temperature as before of this baroclinic wave, and what we have measured, and this is from the velocity field, so we have the divergence, so gravity waves are easily spotted in the horizontal divergence, and we have seen them here. So they basically show up perpendicular to this baroclinic wave in this called entrance and exit region. So they basically follow. And if I show you an animation, that's how they look like. Pretty similar to the numerical simulations that I showed you before. See, they propagate along. Okay, so this was something very interesting. And the importance of this is that we can exclude all our sources that are in the atmosphere. So for example, we know that we don't have topographic generation because we don't have any topography. We can exclude convection. So we know that these waves are spontaneously emitted from the jet because we don't have any other mechanism for these waves to form. Yeah?
How can you exclude convection? Are you sure the temperature is constant over the whole depth?
So we measured temperature with probes along the depths, and we checked for, so we measured during the entire experiment, and so we could exclude that there were no instability, convective instability. Yeah. Yeah. So that shows that these waves can exist and they can generate it by this mean flow. Now, another thing in the atmosphere, which is an open question, is the transfer of energy. So atmospheric spectra here is in the wavelength, and here I'm showing you measured spectra in the atmosphere. So they are characterized by two slopes. So if you measure the spectra at mid-latitudes almost everywhere, you will find this. So you have a large scale spectra that goes as k to the minus 3, and then you have a shallower slope. It goes as k to the minus 5/3. Now, while the k to the minus 3 is well explained by geostrophic turbulence, it's very controversial what can explain this minus 5/3, and even in which direction energy is going. Yes?
How they measure spectra in space? I mean, yeah, it's so
Yeah.
space measurement, right?
Yeah.
It's not made in the,
So, yeah, so they took a lot of commercial flights between Europe and the States, and they fly. And the thing is that it's time converted into space in the approximation that you're going fast enough that it's frozen, right? So, yeah.
So you convert time series in space series
Yeah.
using a velocity.
Yes. So they measure velocity and temperature. There are two velocity and one potential temperature, and they all have the same, yeah. That's a good point. Okay, so there are different theories for this k to the minus 5/3 spectra. There was in the past an inverse energy cascade, convection at small scale and then going upward, and then most likely is energy cascade, so from the larger scale towards the smaller scale and towards dissipation. Oh, okay, sorry. Ooh, wow, okay. Okay, and so one theory actually includes internal gravity waves. Okay, so with the experiment, what did we do? We tried to verify this. So this is our spectra, and okay, we didn't do the transformation, so we did the time spectra, so we have frequency, but if we do the same approximation, we also have wave number. And we do find the two slopes, okay? So great, very nice. But how can we say if what is in the second slope? You need to work out a bit and do a separation. So this is a technique by Oliver Bühler and collaborators. I'm not going to go into the details. But basically what you can do is you can extract the geostrophic component and separate it from the gravity waves component. And what you can see here is the results. So we have that the minus 3 is mostly geostrophic component. And then when you go to the shallower part, actually all the total energy is in the gravity wave component. So this shows that actually the gravity waves can generate this k to the minus 5/3. Okay, 2 words. I have no time, but I'm going to just say that we also use this experiment to do some research in climate change and some aspects of climate change. One question that is still open is whether the Arctic amplification has an effect on the jet stream and what this effect is. Is it getting it wavier, amplifying it, or not? So this is ideal to study in our experiment. We can reproduce the Arctic amplification, so we can have a... okay, I don't know if I should go into detail because I don't have time. Anyways, we can reproduce it, let's say. And the results that we got is that in the experiment, we observe a slower and more irregular jet stream for decreasing difference of temperature. Okay, this is the first result. And then another thing is we studied the consequence for mid-latitude variability. So we can study the temperature distribution. And very briefly, what we found is that the temperature fluctuations decrease for Arctic amplification at the mid-latitudes. Okay, so I'm done with my talk, and I'm happy to have a discussion later, but let me just thank our team, because when you work in the lab, you have a large team of people working with you, our technicians, and then I have Patrice Legal, Miklos Winkse, and Jondan Borcha, and my supervisor, Uwe Harlander. Thank you very much.
So, yeah. So I'm not sure I have understood. So the minus 5/3 that you observe in your experiment is not due to direct cascade of entropy, as you know, is believed in two-dimensional turbulence, but is related to waves. Is that right? I mean, that's your explanation.
Yes.
So, okay, that's.
Just
you-
quickly comment on that. We are far larger scales than Kolmogorov type cascade.
Okay.
This is like, so Kolmogorov would happen at a millimeter, so we are larger scales. Yeah.
Okay, so this is a different So in the data that you show, the one that are taken from the airplane, the minus 5/3 is actually due to gravity or not?
So.
Because this is the important point, right? This is.
Yeah. So the thing is, the picture is more complicated. Okay. So now I'm simplifying things a bit because the two strong theories is either due to internal gravity waves or stratified turbulence. Okay. They both fit the minus 5/3, and it's very difficult to say in the atmosphere. Some models extract and they say stratified turbulence. What we can see from our decomposition is actually that at larger scales, we have gravity waves. And then at smaller scale, most likely, we have stratified turbulence that is dominating.
Okay.
There is another analysis, it's not just coming from this picture. It's a...
But then if it is due to waves, is there some sort of wave kinetic equation that predict such spectrum or not? I mean, is there a prediction from theory that you can make on this minus 5/3 due to internal gravity waves or not?
Well,
sorry.
I'm going to advertise my husband's work. Well, there is some kind of work he did on, so there is not much, so these are interpretation of data fitting, it's not a theory. There is some work he has done on, so it gives a -2. Now you can argue that a -2 and a minus 5/3 are very close and that what you measure could be a -2. And yeah, so there is, Jacques Van Est has worked on this. Yes.
So any other question? I have one question on your experiment spectrum. I saw many peaks, and the red line goes through the peaks, but it seems that you have peaks and like a baseline. So
yeah. So yes. So okay, if you look at this one, this is this is kinetic energy, and this is total energy. Okay, they both fit a -3. So I agree with you. This is because we are doing time measurements. So to measure the large scale, we need a very, very long recording. Now, I haven't shown into this, but we have a lot of measurements for different regimes, and it is for higher rotation, it is less, with less peaks. Yeah. The important part, though, is more this other, like this -5/3. This was just a check that we also have the large scale. Okay, but if you look at the total energy, it's more convincing, probably.
okay. Any other question? We still have time for discussion.
Too experimental.
Oh, I have another question on experiments on the gravity waves. Can you predict the frequencies of the wave, or can you predict the wavelength?
You cannot predict. I mean, the thing you can say is that, okay, thanks. As you explained, the waves are bounded between, we have both rotation and stratification, so they are bound between omega, f, and n. Now, the difficult thing is that we can achieve in the atmosphere we have order 100. So the frequency spectra is spread between F and N. Here we have order 3. So that's the maximum we can achieve. So, okay, no, so you cannot predict, but, I mean, I'm telling you these are gravity waves, but we have verified the dispersion relation. So we have verified, we can measure the horizontal wavelengths and the frequency. We have to guess for the vertical. We can guess a little bit, it's only 5 centimeters, so we have 2 bands, and so I haven't prepared the slide with that, but we can see that between the maximum and the minimum wavelength, they fit the dispersion relation quite nicely. So yeah.
Okay.
Yeah, maybe you have done it, and that's what you are. That's what you meant. But you have space and time measurements, right? In yours, so you could produce this k omega spectrum, right?
Yes.
And you have done probably that to see or not.
To verify the dispersion relation.
Yeah.
Well, I mean, we haven't plotted.
You haven't,
but
yeah.
So of course, yeah.
Okay.
K omega, yes.
K omega. Okay.
And we verified that, as I was
so
saying.
you can tell exactly what is wave and what is not wave, right?
Oh
Because
yeah. I'm not claiming
yeah.
from a animation that these are gravity waves. They could
Okay.
be anything.
Okay.
Yeah.
So it's because you could also filter using this k omega spectrum. You could also filter the wave component with respect to everything else, right? This is what Nicolas does.
One thing is that with respect to Nicolas, which is probably what I have done. What I have done probably. But yeah, we haven't filtered. Well, it's his project, of course. Yeah, so this is very different experiment because we have a very, very large mean flow, which means that we have a huge Doppler effect. And in fact, the frequency of the gravity waves is almost all Doppler shift.
Yeah, I imagine.
So they are transported by this.
Yeah.
And that's a very different scenario than, for example, when you have waves, and you might have vortices forced in an experiment, but, I mean, they are just weakly interacting. So in this case, there are different theories why. One is wave capture, like why the waves are shaped like this, because they could propagate in principle in any direction, right? I mean, the fact that they are generated by the front doesn't mean that they have to propagate with the front. The fact that they are is a specific case where they align. And this is, for example, wave capture.
Thank you.
What is this black line?
That's the wavefront. Here, this blue line, or? Yeah, I just plotted it to show that the waves are aligned perpendicular to the, it's the maximum of the velocity, a streamline. So here is the, So it's a streamline of the baroclinic wave. Yeah.
So the internal waves are following this line. This is what you...
Well, yeah, perpendicular. Yeah, if I show the animation again. Okay, one thing is that the line doesn't move, but it would move with the waves. It was just difficult to plot. But if I show you again, is that they are moving along the line. I didn't move the line. The line is fixed for simplicity. But the initial the line would yeah.
Okay. I got it.
I have no good skills of planning.
I think I missed something when you explained how you checked the dispersion relation, because you said that you only have one component of the wave vector, right?
Two horizontal.
Two horizontal, but then there is one which is missing, right?
Yeah. So so we have a guess, right? So what I did is I took the maximum fitting wavelength for the depth, right? I can guess the maximum. I mean, the maximum fitting wavelength is one wave. And then I can take a guess for the minimum. I mean, I can... Anyways, even if I don't guess the minimum, I can say that they are compatible because they align with the other if I trace the maximum wave vertical wavelength. Does it make sense? I have 3 out of 4 quantities I need to check. So there are the 3 wave lengths and the frequency. Yeah. I can plot the 2, I can take a guess for Z, and yeah.
Assuming that you have quantification of phi over h, which is the h, the depth of the tank. Okay.
Yes. It's a guess, but yeah.
I have a very basic question, like, but this cylinder is supposed to model like a 2D thing or 3D? Like, should I think that this is really like a plot of the object?
Okay, so the baroclinic waves is basically 2D, okay? So you have a 2D dynamics in the system.
So basically the difference, basically the gravity is going towards the center, more or less.
Yeah. The gravity waves.
I mean,
3D.
like you have a hotter fluid outside.
Yeah.
So like, what should be gravity if I have everything in the vertical direction? It's going inside here.
Are these slanted? You have this situation here.
Okay.
Hotter
okay.
fluid. That's what's kept. And then there's baroclinic instability and things, but yeah, that's the situation.
Okay, thanks.
Yeah.
So to Miguel's question, you replied that the number of vortices was a function of the different parameters.
Yes.
What about the waves generated? Are there
The gravity waves, you mean?
Yes.
Huh. Okay. That's a very good question. So, it was 3 years of work to get these waves. No, but I'm saying, so one thing is that this project was combined with numerical simulations. And so the thing is that the experiment should have validated 3D numerical simulations to have all the information and then to do the parameter study. Unfortunately, it was, these are so difficult to measure that in the numerical simulations, they only saw them a couple of times because they were dissipated. They are very weak waves. And so, yeah, the idea was to combine and to compare them, but with the numerical simulations.
They were more dissipated in the numerical simulations?
Yeah. I mean, the thing is this. These are really, really small scale, and they are, okay. These are really small scale, and they are the most energetic. So there are other larger scale gravity waves, which are too weak for the experiment to measure. So in the numerical simulations, they saw the largest scale that had different properties, and they saw only a couple of times these very small scales. So it's not the dissipation, sorry, it's the resolution that was the problem. But I want to say also a few words about the experiment. This helped because we were working in a big project with the aim of actually learning something from idealized numerical simulations and experiments to actually improve the weather forecast model in Germany, ICON. And the thing is that they have learned something. For example, one important message from this experiment is that actually, so first of all, that these waves that are generated at the front exist and are important for the energetic, as I showed, because they can explain this 5 to the minus 3. And these are the ones that are not parameterized currently, because they worked a lot on the parameterization of orographic waves, and because it's very simple, you know which frequency they have, and you know they propagate vertically. And so the model, the parameterization is 1D, or used to be 1D. And this shows that actually it's very important to have a 2D parameterization at higher levels in the atmosphere for parameterizing.
Okay. So we'll sing Costanza for Joe.
Okay. Okay. So the next talk will be given by Michele Dolce, who is working at EPFL in Lausanne, and he will talk about long-time behavior in the 2D inhomogeneous incompressible fluids near a stably stratified Couette flow.
Okay. Thank you very much for the introduction. I would like to thank the organizer for inviting me here. It's always nice being in Rome. Whatever I'm going to talk about, so all that I'm going to talk about today is going to be joint works with Jacob Bedrosian, Roberta Bianchini, who's there, and Michele Dolce. And so basically, I had already a great introduction by the talk of Costanza. And what I'm going to try to discuss today is, as in the title, inhomogeneous fluids, and in particular, I want just to address some relation. So what are the differences really with the Boussinesq approximation? And then I'm going to discuss in detail the Boussinesq approximation at the linearized problem I'm going to consider. And I'm going to tell you probably something about the nonlinear, what we can do in the nonlinear case if time permits. So the equations are inhomogeneous and incompressible Euler equations. And here I'm going to talk, this is going to be a mathematics talk, unfortunately for some of you. Okay, so first of all, let me clarify this. I'm going to assume a domain without boundary, that you should think it is like an idealization of what happens in the bulk of the fluid of basically of the experiment discussed by Costanza. So like you have a cylinder, and here I'm really interested only on what's happening in the bulk of the fluid. So that's why no boundaries, and if you ask me later, I can explain what has been done with boundaries. So I believe basically everything could be done with boundaries. Only on the vertical direction, though. So these equations do possess some problem, clearly mathematically, basically related to what was discussed by Costanza. So here, to me, baroclinic vorticity production is just the fact that whenever I divide this equation by rho, the gravity is not going to be there, and but if I take the vorticity, I'm going to see effects of the pressure, and in particular, there's going to be problem if gradient of the density and pressure are not aligned. So that can generate some vorticity. And so, say a common approximation to study and simplify a little bit this system is assume that the density only matters when generating buoyancy forces, and those is the famous Boussinesq approximation introduced actually by Oberbeck first. And so basically you just think that this is a constant, essentially. But still, this possesses most of the feature of this problem, and in particular also well-posedness is quite a problem. And recently there has been a huge, very nice works, starting with the work by Tarek El-Gindi, that show that indeed even in the Boussinesq approximation there's going to be blow up for the equation for some data. But of course, not having well-posedness in general doesn't mean that the equation doesn't work. We can use them in around some particular cases. So we can really study them, and in particular, what I'm gonna talk about today is like the long-time behavior of Boussinesq, or actually inhomogeneous fluids around some particular steady state. And here, I just mentioned a few names that I'm familiar with those works, and I apologize for all the one I'm missing in this slide. There are many people working, of course, in Boussinesq. So with this, the case I'm gonna essentially try to discuss. So basically, we are gonna discuss stratified fluids, as we saw today, and an example is the ocean, where we can assume that the velocity is 0 and it's gonna be stably stratified, and it's quite concerning that it's getting more and more stably stratified due to climate change, because this is a measure of the Brun-Weisshauer frequency, and is due to the temperature changes, is getting more stably stratified, and that's quite bad because the hot water is going to remain on top for longer times. But a basic example is when you have coffee with milk and you pour hot coffee, you see a stable stratification. Of course, this picture is not from the paper just found it online. Okay. So, what is the specific case I want to discuss today? Yes? This one? Yeah, I have no idea what the green is. I'm sorry. I just know that this is basically the red plot is all of this are measurements of the Brun-Weisel frequency. I don't know all the details really of this paper. Sorry. So what I want to measure, what I want to discuss today is basically when we perturb a steady stratified shear flow. So we add on top a velocity field, a background shear flow, and here let's consider for the inhomogeneous fluids that we have an exponential stratification. And then we perturb it. For the Boussinesq, it's going to be just a linear stratification, which is basically, in some sense, a Taylor expansion of this around the origin. And then I just rescale the density by dividing with the derivative of the background state, and they do define the Brun-Weisel frequency in this way. And for Boussinesq, you have the Brun-Weisel frequency is actually only related to gamma. And then the system takes this form. So the rescale density is transported, is advected by the background flow, and it interacts through a non-local term with the vorticity of in the system. And then there's going to be some nonlinear interactions that I'm not writing. And instead, the vorticity, actually, it's not the vorticity, it's like this quantity. In inhomogeneous fluid is being transported. So the vorticity is not the good unknown for inhomogeneous fluids. But it is in the Boussinesq approximation that where this parameter B is 0. This quantity is being advected by the velocity field, interacts through with the density through this term, and then there is some effect due to the fact that you have a shear flow that generates other complicated non-local terms. Now, you see the difference in Boussinesq in homogeneous fluids in this particular context is just having the fact that you have to redefine your unknown, but once you control this unknown, that's equivalent to controlling the vorticity, as you can directly see on the Fourier side, you can upper and lower bound basically this operator. And now, from now on, I'm going to discuss just the Boussinesq approximation, where you can set B 0, but actually all the results are going to be true for at the linear level for B greater or equal than 0. And the goal is to study the long-time behavior of vorticity and density. So to understand what's going on, let me just consider a simplified case where I do assume that now I linearize the problem, so I neglect the nonlinearity. Let me further assume that I'm in the Boussinesq case with the Couette flow. So I take the simplest possible shear flow, and those are the equations. So advection and interaction through some non-local terms. Now, the system is so simple that even I am able to do a numerical simulation. So here I just do like a perturbation in the density. I don't plot the background states. And I'm putting heavier fluid on here and lighter fluid here. And let's see what happens. So basically at time 0, 1, the effect of the transport, I can say, is negligible. And you do form like two dipoles that are trying to push down this vortex and push up this one. That is what happens due to gravity. And here you also see the streamlines of the velocity field, what's going on. And that's only due to this fact here. So of course, if I start with 0 vorticity, this guy is generating some vorticity. And then if I wait long enough, the effect of the transport is going to be apparent. Here I have periodicity in the x variable, so everything is going to be mixed up and sheared. But there is some interesting phenomenon in the sense that the density is not only advected, it's like splitted, because if you were about to only shear this guy here, you will see something always here at this part, and here no. So something has been splitted. And on the other hand, the vorticity, okay, is like mixed, but notice that the L2 norm of vorticity is growing. So the L2 norm of vorticity keeps growing due to this interaction, and here you don't really see it, but the L2 norm of the density is actually decaying, and the velocity field is aligning with the direction of the shear flow. So it's, in some sense, it's going right, left, a lot of oscillations, but it's getting aligned with the direction of the background shear flow. Now, all of this can be put into a theorem that goes as follows. So this was obtained with Roberta and Michele now 4 years ago. Okay. What are the conditions for the theorem? I need to assume that the Brun-Weiss frequency is sufficiently large. That's related to the Miles-Howard criterion. I will try to mention later why. Actually, this theorem works for inhomogeneous fluid, need not to be the Boussinesq approximation. You do have some regularity, and it works, in fact, for all shear flows that are quantitatively close to Couette in this sense. So you want to be really close to this profile here. And then what happens is that the density and the the first component, the horizontal component, the velocity field, they do converge towards their x average with this rate. And that's sometimes called implicit damping. So there is some damping that doesn't depend on dissipation. Damping in the sense that all the modes but the zero are being damped. So you are aligning with the, with the direction of your shear flow. And the second component of the velocity field decays faster. You can see here, like already at time 16, there is basically no second component of the velocity field. And moreover, we can also quantify the instability by providing upper and lower bounds. In the paper, it's proved only for Couette, but actually now we know that can work for all these flows, up to changing a little bit powers here. And so the vorticity, so the non-zero mode of the vorticity are growing like square root of t. So this can be really put into a theorem. Now, clearly, the upper bounds, we were not the first in noting the upper bounds. The first was probably Hartmann in the 75, where you can analyze basically that linearized problem, solving it with some special functions. And that was done rigorously by Angelin in 2018. And nowadays, we also have a proof by Mark Nolart, a student of Michele, in the channel with 0,1, if you just want to get the upper bounds. So really it's not an effect of not having a boundary. Now the proof of this theorem, where I want to try to tell you now how it works, or at least give you some ideas, is based on an energy method we used with Paolo Antonelli and Marcati to study compressible fluids around Couette. And in fact, this energy method works in other models as well when you have dissipation. For instance, 2D Navier-Stokes Boussinesq, 2D Navier-Stokes MHD that I did last year, or 3D Navier-Stokes Boussinesq by Michele, Augusto Del Zotto, a student of him, and Klaus Wiedmeyer. So, what is let me try to explain how you can prove this theorem. So the idea is simple. So you have this system here. I'll prove it just for Couette, because otherwise it's a mess. So you do have this, this system. Now I take the dx of the density just because then I have all real operators here on the right-hand side. So my variable really will be dx of the density. Then you do a change of coordinates to follow the background shear flow. So you just follow the characteristics. And you do perform the Fourier transform. That's the only reason why you actually need this domain here. If you have a boundary, you have to localize your functions and be careful with what happens at the boundary. But can be done. It's quite technical, but can be done. I haven't done it, but okay. And then you rewrite the system. Now the system, notice that this operator here, 1 over p, corresponds to the symbol of this guy here in the new reference frame. So it's exactly this guy here. And beta square is the one, okay, it's a constant, is there. So you see this system now, if this was not time dependent, you will just have an anti-diagonal system. So these two quantities will live in some ellipse, will stay there. Here you have time dependency. Now, morally, what you can do is just study a second order equation as well for one of the two quantities and use special functions to solve this problem. But that, I would say, is not a super flexible method in the sense that how do I aim at applying special functions for nonlinear problem. So here I would like to understand how to handle this non-autonomous system with an energy method. So here the idea is like, look at this matrix. It has trace 0. So if you were about to compute eigenvalues, it means that we lie in an ellipse if the anti-diagonal term dominate the diagonal one. Just compute from the eigenvalues. Of course, it doesn't make sense when you have time dependence, but you do it. But then you see that this, as time goes to infinity, will actually go to 0. So you lose in which sense this will be dominant. And so the idea is like, okay, let's try to symmetrize the system, keeping the idea that the trace must be 0, and then we want to have the anti-diagonal terms dominating the diagonal ones. And that's what we later called the symmetrization scheme. The idea is simple. You just multiply your quantities, you redefine by multiplying with a weight. And if you want to keep trace 0, it's going to be 1, the inverse of the other. And then you choose the weight so that the anti-diagonal terms are equal. In more general system, you want to have the dominant part of this term equal. And now you have this system here. And associated to this system, again, if it were not autonomous, you would easily find a Lyapunov functional. So you would easily find an energy functional that, if D and A are constant, this is actually conserved for this matrix. And if I want to have that they do lie in some ellipse, it means that the energy function must be upper and lower bounded, must be coercive. And moreover, the anti-diagonal term dominate the diagonal one. And that's true if you satisfy this criterion. Because D over A, a simple estimate will show that is like 1 over 2 beta. So if you are in this regime, that's actually called as the Miles-Howard criterion, then the energy functional is coercive, and it's going to be upper and lower bounded. How do you prove that it's upper and lower bounded? You just take the time derivative of this energy functional. So you just take the time derivative of the energy functional, and you know that if this were time independent, it's actually conserved. So basically, the price you pay is just the fact that this is time dependent. But now, then you have to hope that basically the errors you generate by this time dependence are going to be integrable in some sense. And this is the case because you can readily look at what this will behave, and in fact, you will be able to control the errors. Now, what do you do with this energy functional? So once those variables are upper and lower bounded, it means basically that the vorticity times this factorial is upper and lower bounded. But this factorial is like t to the minus 1/2, because this is t squared, and this is t to the minus 1/2. So that implies that the vorticity will go like t to the 1/2. And the same for the density. This is like t to the 1/2. If this is upper bounded, it means that the density decays like t to the minus 1/2. So basically, these quantities here is just like rescaling properly the system to include all the possible polynomial growth that are there, and polynomial growths are not related to eigenvalues, are related more to non-normality of the operators actually that you had in original variables. So, and this is in fact how you prove that theorem, and here everything is k by k and eta by eta, so you don't need to use the full L2 norms. But this approach is quite flexible in the sense that once you have a good energy functional, you can hope to implement it in the nonlinear problem, and also these variables you can hope to redefine them in the nonlinear problem in a suitable way. But the nonlinear problem, so probably I have 7 minutes. So the nonlinear problem, the nonlinear problem, it has an extra layer of difficulty. Clearly, it's the nonlinearity. And let me try to explain this extra layer of difficulty just considering what happens in the Euler case. So that's something that already is present without any density. And so let me try to explain what is one mechanism that is certainly happening also in this problem. So this is the so-called OR mechanism and the ECOS that goes as follows. So since the velocity field is incompressible, you can try to rewrite the system in this way. So you just isolate the x average of the velocity field and the rest. Now, here is a simulation of Needleman. We know that the 2D Euler equations are conservative, meaning that the energy of the full solution must remain the same for all times. But if you start, for example, you keep going with mixing here, that is what you have in the linear case, then if you were able to propagate this for infinite time, you will lose some energy, because where the energy of the perturbation will go would actually go, essentially, you will lose a big chunk of energy of this guy, and that's impossible. And in fact, in the nonlinear problem, you will see that something is sent back. Something is sent back to recover to preserve the energy, and that's what we call an echo. That's a numerical simulation by Schneiderman. Those were already studied by Van Nest and collaborators in the 98. And basically, the idea is like all the information that is sent towards high frequencies is going to be pushed back to low frequencies, and in particular to the X average, where you can unshear whatever the Couette flow did for you. So this is a well-known phenomenon to the turbulence, that there's going to be a high to low inverse frequency cascade. And in mathematics, you can model this high to low frequency cascade with a toy model. I'm not deducing all the toy model, actually, which was introduced by Van Nest, but just explaining what happens from a mathematical point of view with this unshearing that you see here. Now, assume that you go on a moving frame, then ignore completely this guy, which is actually very physical and important, but for a toy model, you ignore it. And then you see that the evolution of the vorticity now is going to be forced only through the nonlinearity. Write this term in Fourier. This term in Fourier has this form. Now, see that for time eta over k, those are called resonant times, this denominator is 1, and then you have an amplification possibly of a factor eta over k squared. So that means that basically the mod k could be amplified by this factor, and now if the mod k influences the mod k minus 1, that then influences the mod k minus 2, so on and so forth, you will have a high to low cascade, and if all this growth accumulates, meaning that you're essentially doing this unshearing, because you're losing derivatives on a moving frame, so that's basically the unshearing. If all this growth accumulates, worst case scenario, you're gonna lose like square root of eta. That's actually a good indication in the sense that we are not losing too much. Okay, yeah, we're losing a lot, but not that much in the sense that for mathematicians, that's there is room to play in the sense that there's like a Gevrey regularity loss. So we can afford having a Gevrey regularity loss. And that's basically what happens in the 2D Euler equations. Now, for Boussinesq, let me just try to explain briefly what we have. So for Boussinesq, the system is the following. So you have exactly the linear problem as before, plus the X average of the velocity field, plus the nonlinear terms that are exactly this guy here. So now, the X average, even in the best case scenario, you can consider it perturbative at most on a time scale epsilon minus 1 if I start with a perturbation of size epsilon, because that's the natural nonlinear time scale. So best case you can hope is like, okay, I can ignore it on a time scale epsilon minus 1. If I want to go further, if I want to go on longer time scale, I have to include it. I have to handle it. And the idea is simply remove it with a nonlinear change of coordinates. That's morally is like a mix between the Eulerian and the Lagrangian point of view of fluids, in the sense that you're just following what you believe is going to be the leading order flow in the dynamics, so the leading order velocity field. Now, the nonlinearity is going to have at least the echoes instability, because those still are going to be there, but some decay from inviscid damping. And then here we have the further effect that the linearized dynamics is letting us grow, is letting omega and the derivative of theta grow like t to the 1/2. So, if the linearized dynamics persist, when I arrive at time scale epsilon minus 2, this stuff can become of size 1. So I will be out of a perturbative regime. So all the consideration I'm trying to do perturbatively, if the linearized dynamic persists, are not going to be true on epsilon minus 2. And so the claim is that the linearized behavior persists up to this time scale. And that's exactly what we were able to prove with Jacob, Roberta, and Michele in 21. So if you start with the initial data in Gevrey 2 plus, so more than Gevrey 2, to compensate that regularity loss I tried to explain you before, basically you can prove that the linearized dynamics is there. In which sense? You can control the vorticity with a lot of derivatives if you follow the right flow. So if you follow the nonlinear evolution. And the bounds you get are, of course, this epsilon t to the 1/2, because the vorticity is growing. And then you can prove the implicit damping, here adjusted for the x of theta to avoid writing the average. And then you can prove the implicit damping we had at the linearized level. And moreover, you can also propagate the linear instability. So really, whatever you see at the linearized problem is true up to this time scale. And that's non-trivial in the sense that it's beyond the natural nonlinear time scale. So you have to face all the nonlinear problems. Now, in this last 2 seconds, let me just say that last year there has been very nice works doing stratified fluids without gravity. So you simplify the Boussinesq equation without gravity, you remove these instabilities, and you can go all the way up to time infinity. But what's interesting is that Ver and Zhao was able to prove it that in the channel for general strictly monoton shear and densities, and general densities. And so good question. It's like you just remove the gravity here. You just remove this, and you assume that they have a background density that is that changes. Huh? Yes. That's what they can do mathematically. So like once you remove this part, the linear int problem is easier. So you don't have instabilities. Can be studied. Huh? Yes, you still have, but are much milder compared to this guy here. So that's what, in some sense, mathematically, what I see as a, oops, too much. What I see as a difference is that for them it's sort of clear that you have no obstruction in going up to time infinity. For us, we have a clear obstruction after epsilon minus 2 because we have a linear instability. They do not have a linear instability in the setting they consider. So once you remove the gravity, they are able to go much longer. And I do believe it will be actually in possible future direction. Is like I do claim that if you do if you reintroduce the gravity in their problem, you can basically reprove our theorem up to epsilon minus 2 in more general cases. That is my claim. In the sense that once you introduce gravity, you're going to have some linear instabilities that are gonna be there and are gonna force you to stop the nonlinear dynamics if you just want to propagate that linearized behavior. But room for discussion, I would say.
Okay, thank you. Is there any? Okay, there's a question.
Follow up with this question. You said you are a mathematician. It's fine. But is there a physical motivation for looking for such? No. Okay.
Because I'm a mathematician, so I don't know if there is a physical. I would say for Boussinesq, of course, there is a motivation. No, but removing the gravity, I would see is a very nice mathematical problem that clearly gives a hint on what you can try to do on Boussinesq. So it's easier to understand from a mathematical point of view. It's easier to understand, but still it has a lot of difficulties that maybe you will have to face as well in Boussinesq. So Yeah. You exactly. You remove, but for example, there is an extremely nice idea in the paper by Ver and Zhao on how to handle the pressure when you have boundaries. That is, in this paper here, there is an extremely nice idea on how you can treat the pressure term in the presence of boundaries. Because when you have boundaries, everything can be much more complicated, but he has a brilliant idea that basically, if you have a flat boundary and you're perturbing around a shear, you're going to have a lot of terms which are like dx of something. And the pressure, the first component of the velocity field of the pressure will be dx of something. So what Veren does is like, if you are close to the boundary, so here, you can recover the pressure by just taking the dx minus 1 of whatever it was multiplied with dx. And that is like an efficient way of handling boundaries, where basically the pressure is one of the most problematic terms for these problems. And I do believe this sort of idea can be applied in Boussinesq as well, because it's gonna be there. And this first component of the velocity field doesn't depend on the gravity, so it can be nice, just from a mathematical point of view, I would say.
But also in the International Space Station, I mean, if you go in outer space, you can do it. So without gravity.
Okay. Yeah, that's what I'm saying. Okay, I would like to go into the international. Okay. Yeah, but then it's like is compressibility. Can you? Is it okay? Okay.
Michele, sorry, can you, because you mentioned there was an obstacle due to some linear instability, but that's linear after some...
This one?
Because you had a first part where you proved some stability for, I mean, all-time stability for the linearized equation, right, around the base flow, and now you are talking about, here, with this E of t.
Yes, but so these objects are linearly stable.
Okay.
These objects are linearly stable, but the vorticity is unstable. Now, the vorticity is unstable. So, like, of course, like stability depends. So, like, this is like a higher norm, is unstable. And when you go to the full nonlinear problem, in reality, you would like to have an information on theta and omega, and those variables will involve theta and omega, because when you have the nonlinearity, it doesn't go just very well, everything. If everything were about to commute, of course, I would hope to propagate the control on the other guys for all times, but we were not able to do so.
Okay.
It might be.
Okay, it's clear now. Thank you very much.
So, can you come back to the modified energy that... Okay, so, I mean, it's possible to explain, because usually you construct a modified energy, I mean, you want to see some cancellations, right? I mean, so the term Z Q bar, I mean, which cancellation you have with the term? I mean, it's...
No, that's a fair question, in the sense that that's exactly to cancel out stuff, because like...
Exactly.
So once I have a diagonal term, you're going to pick up, when I do the L2 norm of this and this, you're going to pick up the diagonal terms here.
Exactly.
Those cancel out because are anti-diagonal.
So essentially it's a decoupling of the equations up to errors.
Exactly.
Okay.
And then to cancel out this diagonal, you just add this.
Okay, I see.
And this is exactly what you do in first course of dynamical system.
Yes, exactly.
To reduce the matrix.
Exactly.
Instead of reducing the matrix, I just check what's the Lyapunov functional, what's the quadratic form associated to this.
So essentially, if you look for a transformation which try to eliminate the off-diagonal term, then it means that it is generated by a matrix that has 0, 0 on the diagonal and like, I don't know, P minus P on the off-diagonal.
Yes.
Okay.
Yes.
I see.
Just a question as a physicist again. Beta square, also you put that in you discussed that in your last slide, right? So, but in geophysical flow, what is, I mean, beta square greater than 1/4. Physically, is what kind of intuition do we have out of that? I mean, geophysical flow, what is a typical number of beta? And
that's a great question. That's the Brud-Weisshaller frequency. So it's like the effect of buoyancy compared to...
So in nature, do we have cases in which we have...
In the ocean, now it's like 4.
Okay, okay, just that's fair, yeah.
But before it was a little bit... No, so like, yeah, like this frequency is actually increasing. Like you can set it up easily. And in fact, I would say it's a mathematical obstacle we do have now, but I think it's just somebody should sit down and find what's the right energy for smaller parameters. And from a physical point of view, you don't have unstable eigenvalues for the linearized problem once you have this. You are guaranteed that you don't have them.
Okay.
And in physical applications, it's sort of easy to realize. You just increase a little bit your stratification.
Okay, thank you. Michele.
I have just a question about the shear flow that you consider. I think there is something which is very specific about this one, which is the fact that it's one-dimensional, right? And so my question is, what happens when you add some geometry?
That's a great question, in the sense that, so clearly here you have a preferred direction to the shear. Now, this case turned out to be a very good model of a point vortex. Because, okay, you have a geometry, but it's still simple geometry, in the sense that if you have a circular flow, it's still one-dimensional. So, like, and that was proved by Ionesco in GI, in a nice paper up, where basically, for the 2D Euler equation, if you have a point vortex, you have the same equation, but here instead of y, you have like 1 over r. And if you are away from the origin, basically that's the same problem. Of course, putting it into a theorem, it's not easy, but still that's one-dimensional. Once you add some structure, the problem is much harder, even in the simple case of passive scalars. Like deducing mixing properties, it becomes quite complicated even for a passive scalar, from a mathematical point of view, I would say. But it's like if you add, it depends, no? Like basically any Hamiltonian flows will contain some elliptic point if you have some decent hypothesis on your Hamiltonian flow. And around an elliptic point, you really look like just a radial flow. So it depends the question you would like to answer, in the sense that if you are, this one should be like a model of what happens when you have basically streamlines that are periodic and you have a difference in velocity among each streamline. If you have to make a meta theorem. And if instead like you have open streamlines or hyperbolic points, everything is different. Like this sort of picture wouldn't be true anymore. But proving a theorem even for a honest 2D, even perturbation of this guy, it's not okay. Perturbation, yes. This is
yeah, because even though you have this geometry with periodic streamlines, they don't have all the same length, and so it's not easy to perform this kind of Fourier transform and so on, because somehow the length depends on the distance to the point.
Yeah, but here I would say more than the length is actually the period that's important.
Yeah, so when I say the length is the time, the traveling time.
And here the traveling time is different on each streamline for this flow. Because here I'm traveling with velocity 1, here I'm not traveling, or at the center I'm not traveling. I don't know exactly what is the background flow for him. But like at each, since you have y, at y equal 1 you travel with velocity 1. At y equals 0, you don't travel, so you have a stagnation point. So this is really related to the period among each streamline. So what's important is that the period of this, along these streamlines is going to be, the derivative of the period is going to be strictly positive. So you're going to always have a difference in velocity among each streamline. Because if you don't have difference in velocity, you don't have mixing. So mixing is just difference in velocity among streamlines, if I have to put it in...
Yeah, but here you have vorticity, right? So for the point vortex, you have your potential, rotational outside. So.
But okay, for the point vortex, the vorticity is a Dirac delta, no?
Yeah.
So the velocity field is radial.
Yeah, but it's irrotational. It's potential.
Ah, yeah, but also...
Not this one.
Wait,
there is vorticity here.
Well, okay, the point vortex, you have vorticity. I knew that was going to happen. The point vortex, you have, morally, you have infinite vorticity at the origin.
Yeah, but for all the streamlines, you have potential everywhere.
I know, but in the sense, if I look at the velocity field, the effect, how the velocity field is moving particles, is analog to what's going on here. In the sense that just put apart two particles on a point vortex, one will move faster than the other and will rotate. Put a particle along two different streamlines, one will move faster than the other, they will rotate. So that's the analogy I wanted to. It's important to get a result like this, I would say.
Any other question? Okay. So if not, we can thank. And we can go to next talk. On peut prendre 5 minutes de pause. We can take 5 minutes. Okay, so we start again for the last talk of the day. The last talk will be given by Charlotte Dietze. She's doing a PhD in Munich and she's visiting Laure for a few months. And she will talk about forcing and dissipation of waves with the propagators of degree 0.
Thanks a lot for the introduction. Oh, yes, sorry. Okay, so thank you for the introduction, and also I would like to thank the organizers for giving me the opportunity to speak here and also to come to this nice conference. So maybe we should start with the slides. Okay, very good. So my first slide is a bit on what we've seen already in today's mini course, but like a drawing from my side, which is maybe not as nice as the graphs you've seen. So what we are interested in is internal waves, but it will be more a math talk, so enjoy the pictures for now. But I wanted to give some pictures at the beginning at least. So the idea is that we are looking at a stratified fluid, the experiments we're interested in is experiments of a stratified fluid in a tank. And well, the stratification will be by density. So you can imagine, for instance, that you have like salt water, which has a higher salinity at the bottom than at the top. And we think of like some linear stratification because we've seen in today's mini course that this is nice for giving us certain properties and how these waves propagate. And if you have such a stratified fluid, then what we saw is that if you put a fixed frequency, then your internal waves in that fluid will propagate according to a certain angle, which you could compute. But they will always propagate along that angle with respect to the horizontal. This is what I've drawn there in the picture. And there will be some experiments on that. We've seen actually some videos and also a few pictures at least. For instance, in the groups by Mas and Thierry Luxois. And for like one of the main properties for me, which was new to learn when I learned about internal waves, is that essentially the picture you can see on the right, namely if you put just a straight wall, so imagine you have like a rectangular box with your fluid filled, and if you have two wave rays coming in, like the light blue and the bit darker blue one, they get reflected. It looks pretty much the same as you would expect if you had like a light ray being reflected. But then if you put a slope, so this was for instance referred to as topography before, like this is the simplest topography you could think of. What you can see is that if you have, again, your two rays of internal waves coming in, but then they get reflected, and they get reflected in such a way that after the reflection they are again propagating at like this fixed angle alpha with the horizontal, you can see some forcing. So after the reflection they are closer to each other than before. So you have some forcing, some focusing effects. So we also have some forcing, which I didn't mention. So imagine you have a fluid at the beginning which is just like stable, like nothing is moving, and then you put some forcing, like for instance this plate we've seen in today's mini course, to generate some of these waves. And well, what we've seen on the right is that you can get some forcing, and what that will mean is that if you think of the waves getting reflected at the boundaries of the tank, that they can accumulate, or most of the energy can accumulate along some attractors. And I've copied another picture from some physicists. Just pick one of them. So for instance, maybe the picture on the top right. What you can see there is such a tank. There, the slope is in the other direction compared to my picture. But what you can see is that you have a concentration of energy along certain rays, and these will be referred to as your attractor. And what we would like to understand, so this is a picture you see after some time, and what we would like to understand is the long-time behavior of internal waves, like to understand how well these attractors are formed, and also well how you get close to them. And there has been some work on that before. So somehow my first slide was never shown. We directly start with slide 2. So what I'm talking about is joint work in progress together with Laure Saint-Amand, who's here, with Yves Colin Verdière and also Thierry Gallet. And there was a paper by Laure Saint-Amand and Yves Collin-Verdière on this topic before. And what they looked at is following a simplified model. Namely, somehow it's a bit difficult if you think of a boundary and having a reflection. So what they did is said, okay, let's just look at a torus. So we don't have a boundary. And we put some smooth density, which is referred by this dq. And then we look at in fact, a scalar model. So u, which you will see in the black box, this will model our velocity, but it's just a scalar number, but it can be complex as well. And the equation for u is governed, so you have a time derivative of u, and plus I times h of u, where I will explain in a second what h is, will be equal to some forcing f times forcing frequency. Now, what is this h? This h will be a bounded self-adjoint operator, and we put an I times h so that it's anti-adjoint. So if you take its adjoint, you get a minus sign. And moreover, it will have many nice properties, which I don't want to recall in detail here. But one of the things you should imagine is that h has continuous spectrum, and maybe there are a few eigenvalues, but certainly not eigenvalues that accumulate anywhere. And if you want to have an example, you could think of just h being a multiplication by a nice function in space. And in fact, we will do an example on the next slide. Okay, so also what I haven't, well, I've told you about the first equation, evolution of u, and what we start with is u at time 0 is 0, which corresponds precisely to the situation where your fluid at time 0 is just at rest. And the question we are interested in is what happens if you wait for very long times. Okay. Now, I said they have some results on this, and this will be in 2 slides, but let's first look at the example to get some feeling. Namely, the example I would like to look at together with you is, first of all, it's not really a good example because I want to look at x being equal to r, so it's not a torus, and it's also not 2-dimensional, but let's forget about that. And then the operator h will just be the multiplication by x in my case. On the previous slide, I wrote it should be a pseudo-differential operator of degree 0, it should be bounded self-adjoint. Well, this will all be satisfied for this one. And then for the forcing, I assume that it's a very nice forcing, namely if I go to Fourier space, it will be a nice compactly supported function. And moreover, for the forcing frequency, and this is maybe a bit unintuitive, from a physical point of view, is that you can make a change of coordinates where you will change your operator h. You can always assume that the forcing frequency lambda 0 is just equal to 0, because you can change your function u. Okay, so if we have this model which we had before, so I copied the blue box we had before, then in Fourier space it looks like, well, the blue box I have on the left, so the time derivative of the Fourier transform of u minus the derivative in the Fourier variable of u had is equal to the Fourier transform of the forcing, and at time 0 it's equal to 0. And the good thing about this example is that you can solve it explicitly. And well, I've written down the solution here, so the Fourier transform of u will be given by some integral over the Fourier transform of the forcing in time, well, starting at frequency xi going until xi plus t. And now I said I'm interested in long-time behavior. So let's just take the limit t going to infinity. Well, in this case, this should converge to just the integral from xi to infinity of the Fourier transform. And well, this will be my u hat of infinity, and I've drawn a plot of this u hat of infinity. So what you can see is it will be constant for very negative values of xi, and then will go to 0. And well, you can also undo the Fourier transform, and then locally in x space, it should have a singularity like a 1 over x near 0. And some property, maybe I should go more to this side. Okay, some properties of this u infinity are that it's not an L2 function. So you can see this by just looking at the Fourier transform, which is like a constant somewhere. This won't be an L2 in general. But it will be in some Sobolev space, namely h minus 1/2 minus. And if you're not too familiar with this notation, then you can just look at the line afterwards. So it means that if I integrate the Fourier transform with a weight that depends on psi, that decays, then this integral will be finite. Okay, and well, as I've said, so if you want to find the u infinity just directly, you can also just look at the equation and imagine the time derivative being 0, so this will look like f of x divided by x, roughly. And another thing you can see is that if you look at the L2 norm of u in time, at every fixed time it will be in L2, but it will grow roughly linearly. So you do have a function u of t that is in L2 for any times t, but in the limit, well, the limit won't be in L2, but rather in the sublevels space h minus 1/2. Okay, good. And now if we believe that, well, all of this can be generalized in this setting, and this is what Laura and Yves did, and they got a result of the form. So maybe let's look at the second point first, that if you multiply u by your phase, so think of lambda 0 as being 0, then you don't have it anymore, then you will get a u infinity, which is this limit we looked at previously, which will be in the sublevels space h minus 1/2. Plus there will be a term which is bounded in L2 and some small corrections. So you get some precise decomposition of what your function will look like for large times. And another thing we've seen, and this is the first point, is that the L2 norm will grow roughly linearly in time. And this is also what they could prove rigorously. Now what that means from a physical point of view is that the model, since I said we think of u as being some sort of kinetic or velocity, that means that we can accumulate an infinite amount of energy as time grows. However, in the physical models, this is not quite what we would expect, because you have dissipation effects. So for instance, coming from viscosity. And these will make sure that your system will not accumulate an infinite amount of energy. So just to recall, where does the energy come from? It comes from the forcing you put, because you always put some forcing all the time. Okay, and so our main goal is to understand, or to try to see how much, what we can do in the case where we add viscosity to the model. So we take the same model as before, which is in the blue box on the top, and we would like to understand, if we add viscosity, what is the long-time behavior of our system. Good. And now this is the orange box up here. So I added the term minus nu times a Laplacian of u, which models the viscosity. And again, in the example we looked into, you can again do the analysis. It's a bit more complicated, but for instance, you can still write down the solution, which I wrote at the top. And well, there are a few things you can see. For instance, first I said that the f hat should have compact support. So if the time is really large, then this means that in the variable eta we will integrate over the whole support of f hat. Now, what about the exponential factor we see afterwards? So this is something we've seen also, I think we might have seen that as well in the mini course, or something related to this, that in the exponential factor we have a minus nu, and then there is some integral from psi to eta, but well, this will only matter if it's multiplied by an eta, for those eta where we are in the support of f hat. So the term from the exponential will give me roughly some minus nu times psi to the 3, because we integrate a square function. And so this gives us some damping, or also gives us some indication on where the psi variable roughly lies for the length scales. But I will come to this point later, also on the next slide. And the guess in this case would be that, or what you can prove in our simplified model, or in this very simple example with multiplication by x on R, is that if you look at the L2 norm now, that in fact your viscous solution will converge to some limiting solution, the u nu infinity, which would be, well, you take the solution I've written up there and you take the limit t to infinity, and this will be in a uniform way at a certain time scale. which I will come to. And the time scale is something like order nu to the minus 1/3. And for the solution u nu infinity, it will, so we've seen the u infinity previously, which was like this 1 over x, so you had a singularity at 0. And now what will happen for the u nu infinity is that it will look like our u infinity, but only for moderate frequencies, namely only for frequencies which are up to, say, nu to the minus 1/3. And then there will be like, it's not a boundary layer, but certain layer part, which regularizes, so which doesn't have the singularity, which we call u layer, which will be at smaller scales. So these will correspond to the frequencies which are larger than nu to the minus 1/3, or in X space this will be at scale nu to the 1/3, which will be small in h to the minus 1/2, and then there will be some small remainder. And the first goal, the first thing one would like to understand before understanding the solution for large times is just to say, okay, let's just try to understand this limit u nu infinity, which you can express differently by applying the resolvent, the viscous resolvent you can see in the very last line. So you take the inverse of the operator I times h minus lambda 0 minus nu times Laplace. So the way you get it is you take the orange box you have up there, and in the first line you just cross out the time derivative, and then you solve for u nu. Okay. Good. Now you might ask yourself, so I had this scale nu to the 1/3 several times, and one question you might ask is where does it come from? So we've already seen it in the example, in the exponential factor. But another way of seeing it is that you say, well, at very large times, what should happen is that the effect coming from the dissipation, so from the minus nu Laplacian, and the effect coming from the Hamiltonian flow should average out, because you will converge to some limit. And, well, in more mathematical terms, what that means is that, well, from the Hamiltonian flow, we just think of it in terms of classical mechanics, so it will be some Poisson bracket. And if we think of the example we had, but also you can make sense of this in a more general sense, is that from the Hamiltonian flow we will get some contribution which looks like a derivative in psi of u hat if we go into Fourier space. And from the viscosity we get a nu times psi squared, which is just the Fourier transform of the Laplacian applied to u hat. And so what we will see is that, well, if you think of the derivative of psi like a 1 over psi, then you see that nu times psi to the 3 should be of order 1. So this is where interesting things happen. Or put differently, psi is of order nu to the minus 1/3. And now, in the same way, so before I said something also about how fast things converge to our limiting solution. In the same way, you could ask, what is a good time scale? And the relevant time scale in this case can also be seen from the equation we have. Namely, if we think of the dtu as just a 1 over the relevant timescale, and then what we end up with is that the relevant timescale is like nu to the minus 1/3. So this is how we come up with these scalings. Okay. Good. And now I will present some things which, or I presented some things which we would like to prove, and here comes something we could prove. Namely, it's an estimate on the viscous resolvent. And the reason why this is interesting is, I said, well, maybe the first goal is to understand the u nu infinity. And this was nothing, so this is what I wrote in the very top right corner. This is the viscous resolvent applied to our forcing F at frequency 0. Or, well, okay, let's not worry about the frequency, but this is the viscous resolvent applied to F. Okay, so if we understand some properties on the viscous resolvent, then we automatically, if we think of F being a very nice function, we get some properties on our solution at large times. And, well, the statement we could prove is as follows. So if we think of this viscous resolvent as an operator from the L2 space to the L2 space, then what we could show is that its operator norm is bounded by a constant times nu to the minus 1/3. Now, this is not quite correct. We have to put some minus 1/3 minus alpha, where alpha is some small constant. Think of this being almost 0. And the big constant, capital C, depends on lambda and alpha in a nice way. So in lambda it will be continuous, and well, I think in alpha we can make it continuous as well. And moreover, we need that lambda is not an eigenvalue of H. And well, what goes into the proof will be some genericity assumptions on H, which I swept under the rug because they are maybe a bit horrible to read, but it's nothing too wild we would expect. Now, as a consequence, I said we prove this theorem in order to find something out about the U nu infinity. As a consequence, what we can see is that the L2 norm of U nu infinity would be bounded by nu to the minus 1/3 minus alpha. And in fact, if you think of this whole scaling argument we had before, the optimal thing, or what you would expect in an ideal world, would be nu to the minus 1/3. So in a way, it's not just any estimate, but it's almost optimal. Okay. However, one thing, now this is what we can show. Now there's one thing which we cannot show. What we would actually like to have, so before I stressed this space h to the minus 1/2 a lot, which seemed to be the right space for looking at the U infinity, but also the U nu infinity. And so what we would actually like to have is an estimate in h to the minus 1/2. Because what we would expect is that for the h to the minus 1/2 norm of U nu infinity, that we can control this uniformly in U. And what this would correspond to is some estimate of the viscous resolvent where it goes to the space h to the minus 1/2, and say we allow ourselves for h to the minus 1/2 minus epsilon. And well, we want this as an estimate of some operator from some space to another. So for instance, you could start with h 1/2 plus epsilon. But f is very nice, so you can put anything there. Yeah, but this is something we cannot show yet. And depending on time, so I have to see how much. Probably I don't have any time left, right?
Yes, since we started 15 minutes later, we still have 5 minutes.
Okay, good. Then maybe I can give you some hints on. Yeah, I don't think it makes sense to give hints on the proof in 5 minutes, so maybe let's skip that. Also, I think people are maybe. I can tell to those people who are interested later, and maybe let me rather talk about some open questions and then summarize. Okay. So, well, one open question is what we've just discussed. Unfortunately, I made some mistake in writing the slide, so forget about the nu to the alpha on the right. So one open question which we would like to address in the future is whether we can get some bound on the viscous resolvent, which is uniform in nu, because it would allow us to get some good information of what happens at infinity. But also this would be a valuable tool for the analysis we would like to do in order to really understand the solution U nu at a certain time t, which is large. So this would also be a tool for finite time, but very large time. And another thing we looked into was to try to understand this behavior of the solution at large times. And for this, one question we came across is for the attractor. You saw on one of the first pictures, so this was this picture taken from a paper from physicists. One thing you could ask is whether if you turn on your viscosity nu, how this affects the attractor, whether it will stay the same or whether there will be a certain shift, how it will behave, because this would be an important information for getting the right ansatz, even for trying to find an approximate solution for large times. Okay, and so with this, I want to summarize. So what we're interested in is large time behavior of internal waves, which have some forcing, and we want to look at the case with viscosity because it means that our system will not accumulate an infinite amount of energy, and is, well, the thing you see in lab experiments. And so far, what we've been able to show is this bound in the red box you can see there, which gives us some information on what will happen for the viscous solution at time infinity in an L2 norm sense. Yeah, but there's still a lot of things to do, so I would be happy to discuss with you and afterwards, and if you can share some insights. Thanks.
Some question?
So thanks for the very nice talk. And so first I have a little remark in the sense that once you have this resolvent estimate, you basically also have like a decay for the semi-group associated to IH minus nu delta.
Yeah.
And then my question is like, how fundamental is that you have a Laplacian? In the sense that if I take an advection diffusion equation with an Hamiltonian velocity field, I can easily find the IH by going in action angle variables, but then the Laplacian becomes a disaster. So like, do you really need the Laplacian, or what properties you need on that diffusive operator?
So anyway, since somehow we don't have the very like, since we have a density and so on, like in a way we already have some geometry. So I don't think that you need like precisely the Laplacian. What do you need? Something which behaves like two derivatives would be nice, but I'm not. I think you could probably also try and see with like other orders of derivatives and try to do the analysis.
Or even maybe some non-degenerate elliptic operator with some coefficients that depends on the.
I think you could try to do that. I don't think this would be a problem. I would have to check carefully, but I don't think this would be a problem.
Okay, thanks.
Thank you. Okay, maybe first my question. So you were mentioning the attractor. How is it related to U infinity? Is it singular support or something like that?
So it's where you have the like. In fact, the attractor will correspond to the wavefront set of your U infinity. So it will be both like where the attractor is located and also
at which
the
frequency?
directions. Yeah.
Okay, thank you. And also, yes, I was planning a question about Moore's theory, and so you mentioned it because it looks very much like the kind of estimates I think given by Moore's approach. And I don't understand because from what I remember, one big field of application of Moore's theory is for Schrödinger operators with the Laplacian. So what do you mean when you say we should try to develop Moore's approach for...
Okay, so when you have Moore theory with the Laplacian, then you also have the small parameter in front of the Laplacian?
No, not necessarily a small parameter, but that's what you mean. You mean for vanishing viscosity, Moore's theory for vanishing viscosity or something
at least
like that?
you want to be able to keep track of how things depend on your parameter nu.
Okay, so something more quantitative, you mean?
Yeah, but still maybe we should discuss.
No, I don't know so much about it, but I think this is the kind of operators that is considered in Moore's theory without the small parameter maybe, but still one big field. Okay.
Any other question?
I do have a technical curiosity, like, because I'm more familiar with these resolved bounds in passive scalars, etc. And how do you gain here? The trivial bound will be nu to the -1 of the resolvent. Where do you have the gain with H, with the interplay between H and the Laplacian?
Maybe I go to some slides I skipped. So where do you have the gain in H? Like one gain in H is something you get, in fact, from Moore theory. So maybe that's on the next slide. So there you definitely get some gain, and then also I think it's more that you have both the H and the minus nu Laplace at the same time, and maybe sometimes one of them helps, maybe the other. So for instance, you have this bound in the purple box there, where you can bound some gradients by the operator, and I think this is somehow, morally speaking, where.
But like basically, this is the real part is what will give me the nu to the -1, and the imaginary part will be the.
Yes.
In some sense, like.
Yes, but
because usually what I would do is like, and do some cutoff to localize where H is actually playing a role.
Yes, actually, this is what I wanted to tell next. Yes, so we do localize in H in the spectral subspace. So we localize at where we are close to our value lambda and where we are far away, and we treat both terms separately. And I think this is where you can also gain from.
And the alpha loss is this log, no? Or no?
Yeah. Well, yes.
No.
Plus also the fact that you're from the Moore theory, you are an H to the -1/2 minus epsilon. So from this and Sobolev interpolation, you will also get a bit of loss.
Thank you.
I have a question which is probably not very clear, but I will try.
Okay.
In the experiment, the length of the attractor is important. Because the length of the attractor. Because if it is very long and the dissipation is strong, you will not be able to close. Where the length of the attractor is hidden in this? It is in lambda?
So in general, where the whole geometry of the attractor and so on is hidden, like in this proof, this is more like a spectral theory proof, but it uses one key ingredient, where a lot of this geometry and the attractor is hidden. Namely, this is for the Moore theorem in this box at the top. So this comes from the paper from Laure and Yves, where they really did some local normal form and check that you actually have all the properties satisfied, so you can apply the Moore theorem. And there you also have like the different lengths, but I don't think we really see them depending on the nu that we treat them differently. But I would say where the attractor is hidden is inside the Moore theorem.
Thank you.
I think actually there are two things. That there is one parameter which is not explicit here, but which is just the contraction along a cycle, which is so. But it appears in the constant here in Moore theorem, and I think that the other